Okay.
You should be host now.
Rock and roll.
Thank you.
Very good. Thank you very much, and enjoy the workshop.
Thanks. Arno, you can now rename yourself, I think, if you wish to.
I can indeed.
Oh, I think we should have asked him about the YouTube situation there. But I assume they're gonna.
Well, he's still there, isn't it?
We will be fixing the YouTube shortly.
Oh, okay. Okay, yeah, you are still there. Okay, great.
Yeah.
Awesome. Thank you.
We will be fixing that. Thank you.
So, I have my full name now.
All right, perfect.
Right.
Ooh, we have another co-host.
Richard, you're now a co-host.
Thank you.
Testing, see if you guys can hear me.
Can you guys just hear me fine?
Yeah, you're a little quiet, but that's okay. Maybe you're a little quiet.
Oh, that's a good question. My audio is okay as well?
Yours is fine. Yours
Perfect.
is a little bit louder than Kevin's, but they're both fine.
This is Brian. I don't know if you can hear me.
Yes.
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 Good.
Very clearly.
Since I try using Zoom instead of YouTube today.
That's good, because that's the only way you can share your screen.
Yeah, I'll be in a different room because my wife has a purple wall, and being Lidos, I'm presenting in front of a purple wall.
You can also, if you have an image, you can upload it to Zoom and set it as your background. Like I'm not actually in front of this bucolic scene at this moment. I'm in my daughter's bedroom. She has lived here for 10 years, so not getting a lot of heavy use.
I don't dare to try and change that. I think you have to do with my background, which is just a baby room.
Oh, there's a nice background. Is that Munich?
Looks that.
No.
Yeah, that's my hometown.
What's it called? What's its name?
Amersfoort.
I thought so. It looks Dutch, so
It is, yeah.
we are very close actually.
Really?
I'm in Soest.
Soest? Yeah, that's about 10 kilometers from here.
Yeah.
Wow.
Yeah.
Coincidence.
Small world.
Nothing in the U.S. is only 10 kilometers away.
Like Canada.
Canada, nothing is 100 kilometers away. Canada, you got to go 1,000 kilometers to get into civilization.
Pretty much. We all live within like 200 kilometers of the U.S. border.
I suppose.
Yeah, I guess it's also history because people here used to live where they worked. So you would almost certainly live in the city that you were working.
Nice.
The only way for transport was by horse or carriages. So that's why the old cities are always very compact, very close together.
Interesting.
Yeah, whereas the U.S. was very much developed with cars, so we have very sprawling cities.
Certainly,
Exactly.
L.A. is an example of that. Los Angeles.
Yeah, I know.
Yeah.
Boston's more sort of the old style to some extent.
Yeah, Boston's nice.
Yeah, I've been there twice. Nice town. In fact, I've been trying to visit lots of old towns in the States, and very nice to see what the settlers did there. Especially if you look carefully, you can find some old villages, but sometimes they were quite remote because they were either deserted or not very convenient for traveling.
Yeah. Well, Savannah, Georgia is a very nice old town, as is Charleston. And there are also some old towns out west, as we used to call it, that were mining towns. Bowie is sort of famous as being what's now called a ghost town because there's nobody there, but they're interesting to visit.
Calico, I think it's more of a tourist attraction.
Yeah.
It's also I think it's in California.
What's it called?
Calico.
Oh, Calico. I haven't heard of that.
You know, they have train rides for kids and stuff. Looks like it's an old Western town.
Where the gunslingers met
Yeah,
in the middle of the
Yeah.
main street. This town's too small for the both of us. Okay, I'm going to share my screen. First, I guess get my screen set up. I totally messed up my sharing last time. Hopefully I won't do it this time. Let's see.
It took me a while to catch on to that. I was
Well,
I
I'm
was
glad.
focused onto what you were saying, and then Sarah sent me a message and was like,
Well, my daughter sent me a message too, and I didn't even see it.
"Oh."
So that was a sharing issue. I did a test run with my wife's Skype last night. So I hope when I get to my turn, it all works.
Yeah, the problem is that when you share, you can either share your whole desktop, which is the safest thing to do, or you can share one individual screen. And I shared one individual screen, and then I went into present mode, which created a different screen. And so people were still looking at the original screen. It depends on what step you take between sharing your screen and showing if you don't do anything at all, then it works fine. But if you click the wrong thing, you now have a different screen in front of you. Whereas when you share your whole screen, what you see is what everybody sees, which may or may not be good. Okay.
I've got YouTube up on another screen here so I can see for sure what I'm doing, but you need to have a few monitors hanging around, I guess.
Yeah. Okay, let's see, where am I here? So I'm going to now share my screen. Can you see that?
This looks
Yep.
good. Yep.
Yes.
Oh, it looks like we're live on YouTube, but that link is a little weird. Yeah, so there's 2 Splash 4s on YouTube. I just saw this. And the one link on the main page is the wrong link. It goes to a previous stream. So,
Say the main page. Do you
yeah,
mean
if you go to the
program?
the program page on the Splash site, that link is wrong.
Okay.
So, I guess we can share it in Clouder, but
I'll fix it.
oh, okay, you've got that. Oh, I
can.
that means I have access to there, don't I? I'll let you do it.
So it's the Tuesday HILT YouTube is not correct. Is that what you're saying?
Yes, but I've got to get the right link to you. I've got like 2 machines here, and so it's like yesterday I had 2 mice on the desk. Somehow managed to make that work. But, okay, so what I'll do is
This is going to be really inconvenient. Oh well.
I've got a
He
plan
didn't quite
here.
figure this out. Having us in 2 different rooms was clearly a mistake. Let's see. Okay.
Because so what happens is that we're actually that link on the page. There's a coming up next, which is the actual live now Splash 4. Anyways, I'll get the link here on this machine. Send that in a message. Coming right at you.
Okay.
There, that's the right one.
there. Where did you send it? In
In
Zoom
the
chat?
Zoom chat, yes.
Okay. See if I can copy it.
Oh, it looks like one of the ACM people posted that link into the Clouder room as well, so that's helpful.
Okay.
Just saw that.
Fortunately, I copied it about 6 different places.
Can you hear anybody talking in the background through my mic?
Nope.
Okay. My girlfriend's also in meetings, so I was forced to work from home, so I can hear her through the wall. But you don't, so that's good.
Yeah.
My daughter is scheduled to wake up just about when I do my presentation. So
Oh, good.
I'm going to quickly head to the toilet one more time.
Yeah, I'm also in NATO meetings sometimes, and especially doing the online version where people live in either the western part of the States and in Australia. Makes it a bit tough to get a part of in time where you can actually both be awake. So it's either very late or very early.
Yeah. So Drew, do you have some slides you're going to show?
His mic is muted.
Yeah, I am not well versed in the ways of Zoom, I'm afraid. Yes, I do. So let me figure out how to share a screen here.
Yeah, I'm going to just, let me just introduce you first, and then I'll let you take over.
Okay, great.
I'm going to wait another minute or two. Can you see those that slide?
I can.
Yes.
Okay. So I guess we'll get started. I want to welcome everyone to the second day of the HILT 2020 workshop. In the grayed out bullets there, you can see what we did on Monday, which was focused very strongly on parallel programming and particularly the OpenMP standard infrastructure for supporting lightweight parallelism and its availability in various programming languages, C, C++, Fortran, and there are other bindings to OpenMP. In particular, we talked about the forthcoming Ada 22X binding to OpenMP, and some lower level issues of how to improve the job of the compiler of a program that uses lightweight parallelism by making some small additions to the compiler IR. Anyway, today we're going to focus at a little bit higher level and perhaps more focused on distributed programming. And but before we do, we have a word from our sponsor. This is SIG Ada has been sponsoring this conference and this workshop over the past many years now, 15 years or so. And every year, SIG Ada gives out a couple of awards representing both community, contributing to the Ada community and also contributing specifically to SIG Ada. And we have the president of SIG Ada with us, Drew Hamilton. And Drew has a couple of slides and he will make the awards and then we'll get into our keynote. So Drew, can you share your screen?
I think so.
Okay.
Let's see. Oh, okay. Sorry about this. Can you see my screen?
Yes, now we're hoping you'll bring up your slides.
Well, yeah, that's next baby steps here.
Next step.
Apologize for that. So
Mississippi State, all right.
on behalf of the SIG Ada Awards Committee, it is a pleasure to announce the following awards. The first is the Robert Dewar Award. This year, the purpose of this award is for broad, lasting contributions to ADA technology and usage. And this year it's awarded to Randy Bruchart from R&R Software, Steve Baird from Ada Core, and Jeff Cousins. As the citation reads,
can you bring up the citation? We're not seeing it.
You're not?
No.
Oh, you're seeing my, I'm sorry. How's that?
There we go. Okay.
About that.
Good.
As I was saying, Steve and Jeff are leaders of the ADA Rapporteur Group. Randy, as the editor of the ADA Standard, shepherded the 2020 X revision of the ADA Standard to near completion. So nearly a decade of challenging, exacting, and in some cases controversial efforts. Full support for lightweight parallelism, along with first-class support for user-defined data structures, both user-defined literals, image attributes, aggregates, parallel iterators, and other capabilities, and improved specification capabilities for pre-post conditions, global variable usage, and the potential for blocking of maintained ADA's position as a preeminent, safe, secure, high performance, and high productivity language for most software-intensive systems. So, yeah, it's a pleasure to announce that award, and the recipients will receive their hard copy award, after the conference. And so, congratulations to 3 of them. The next award is, I think, even more significant because the Distinguished Service Award goes to Frederick Taft, and it has been. And you've had to put up with some of the technical glitches from me because we're trying to keep this close hold, which is really difficult because Tucker is such an instrumental part of SIG ADA. So apart from being heavily involved with the ADA programming language and its evolution since decades before, S. Tucker Taft, aka Tuck, has been very active in ACM SIG ADA for many, many years. And when we say that, I've been a member for 30 years. And I'm not sure that, I think there are a lot of our members that are have considerably more years of service than that. Initially as presenter of papers and tutorials at SIG ADA conferences since 2013, also as one of the elected officers in SIG ADA's executive committee in the function of vice chair, earlier called vice chair for meetings and conferences. Since 2012, Tuck has been the main driving force in establishing the HILT series of events focusing on high integrity language technology. First, the 2012 and 2013 HILT conferences in Boston and Pittsburgh, respectively, as the continuation of SIG ADA's annual international conferences. Later, the biennial 2014, 2016, and 2018 HILT workshops in Portland, Pittsburgh, and Boston, respectively, co-located with major events such as Splash and ES Week. Even now, in these strange COVID times, Tuck is organizer of the 2020 online HILT workshop, virtually co-located with Splash 2020. For his role in and service to SIG ADA, and for his tireless efforts to create and organize the HILT series of events, make them visible to wider audience, Tuck deserves to be recognized, and thus is our prime candidate for ACM SIG ADA Distinguished Award. And I echo the award committee comment. This has been long overdue. So
I'm very flattered.
Give me a chance to thank you publicly for everything you've done. Thank you very much, and congratulations.
Thanks, Drew. I didn't have any idea. Okay, well, on that,
we kept
that
it
note. Thanks, Drew. I encourage, let me just quickly share my screen one more time, and I'll introduce our keynote speakers. The length of the hair by one of them, Arno, has gone up and down. I've had 2 different pictures up here, and now I think the earlier one was closer in length of hair, but my hair also has been growing and shrinking. But anyway, Arno Lundstra is one of our keynote speakers, and he describes himself as an artist, a researcher, and an entrepreneur curious about new possibilities with new technologies. Our second keynote speaker is Kevin Sapper, who's a software consultant and an enthusiastic ZeroMQ community member. My own view, to some extent, in why I've invited Arno and Kevin to present on ZeroMQ is I see we learned a lot about OpenMP, and it's sort of the default standard for doing parallel computing these days. I think ZeroMQ maybe already is or will in the near future become this sort of equivalent standard for doing distributed computing in the wider world. I think there are other standards like OpenMP and so on that are used specifically in high performance computing, but I think ZeroMQ is more available and easier to use for the wider audience for distributed computing. So with that, I will now let Kevin and Arno take it away.
Well, thank you for this introduction talk, or should I say talker? Yeah, thanks. We're presenting this together, my colleague Kevin and I. I'll introduce myself quickly. As Tuck already mentioned, my name is Arnold Loonstra. I'm a researcher at the HKU, University of the Arts in Utrecht in the Netherlands. And specifically, I work in the expertise group we call the for creative technology. And I'm involved in the ZeroMQ community for quite some time already. Can't really recall when I started, somewhere 2012, I think. Yeah. So that's me, and I will co-present this today with Kevin.
Yeah, my name is Kevin Sapper. I'm currently working as an IT consultant at Concentric in Germany, and I'm also involved for almost 8 years now in the ZeroMQ community. Actually started as a student when we were trying to build a peer-to-peer Dropbox replacement, and used that and decided to use ZeroMQ for our student project. And yeah, that's how I got hooked into the community and into building distributed and systems with ZeroMQ.
So yeah, we'll start a little bit with the history of ZeroMQ, and then we'll quickly get into the more technical stuff, and hopefully leave enough time at the end for Q&A. So, but let's quickly start at the beginning. So ZeroMQ started live in around 2007 as an iMedix project to build a low latency version of AMQP messaging product. So Cisco and Intel were partners. From the start, ZeroMQ was focused on getting the best possible performance out of hardware. And well, the first commit is of 2009. So I'm not really sure what happened from 2007 to 2009, but I cannot find it in the Git repository. So anyway, but if you dive into the history of ZeroMQ, you will find two key public persons, Martin Soestrik and Peter Hintjens. Martin being the technical lead and Peter more focused on the community and usability. And also being the visionary behind what ZeroMQ is today. Peter is also the author of the famous ZeroMQ guide. I have it here. It's also online for free. A highly recommended read, actually. So next slide. So like I said, we'll get into the technical stuff in a bit, but you need to understand that ZeroMQ is meant to be extremely performant while being very easy to use. The use case it was built on was, at least from what I understand, the financial exchange markets, in which throughput and latency is of utmost importance. It also was started out of the experience of building AMQP. They wanted something more simple and more powerful. So, yeah, if you want to build and grow distributed systems, things need to be simple. And as a nice anecdote, in 2011, CERN selected ZeroMQ for operating their accelerators. They tested a few alternatives and ZeroMQ scored highest. So originally the zero meant no broker, no latency, or zero latency. But through time, it also meant things like zero administration, zero cost, zero waste. Overall, it means a culture of minimalism. And I personally like this a lot. I have to deal with concurrency, and yeah, in my opinion, that gets complex really easily. So I really like simple and elegant solutions. So that's a bit about how ZeroMQ sprung to life. But ideally, it would be Peter telling about ZeroMQ, and not me or Kevin. Peter was a great speaker, and I might say kind of an open source celebrity. I personally think he was that kind of a rare person that has had a huge impact on the open source community. Unfortunately, Peter has passed away too early, and well, we as a community are continuing in his vision. So, but besides ZeroMQ being an important technical accomplishment, in my opinion, Peter also realized for it to be successful, it needs a thriving community. So, well, technology can change all the time, but it is actually the community that holds it together. A project is nothing without users, and an open source community actually thrives on contributors. So Peter actually devoted quite some years into detailing the mechanics of open source communities. You can look up, you can look talks of him on the internet. You can find them. There's many talks about this topic. But yeah, we're now at the HILT workshop at the Splash conference, specifically about distributed computing. And well, I think ZeroMQ was built for this. But what is really important to understand about distributed systems, normally I could ask the audience, but that's a bit weird now, is that in a distributed system, things happen at different times. So, and at different places. So time and space are broken up. And I send a message, it will arrive in some unknown future in an unknown place. And it's crucial to build for this, to design around this asynchronous characteristic. And in doing so, you will find the same patterns of communication emerge. These patterns are actually built into ZeroMQ, and we'll discuss them further on. But what I kind of like to say, explain as well, is what Peter also realized is that these patterns are also key ingredients to a successful community. And with a community, we could also mean a company or a corporation or an institute, whatever. It just implies people or systems working together. So these ideas are also applied to the ZeroMQ community. And myself, being a member of this community is because of this. So, but is a key ingredient then is how we agree to work. So this is just as essential for a distributed system as it is for a community. Therefore, the protocols, the contracts for how we agree to work are essential. And this is obvious how this works in distributed systems. But again, it also applies to communities. So yeah, how can a distributed system scale? How can I participate? It has to be very cheap. It has to be very simple, and it has to be very welcoming. A simple example is the effect Git with tools like GitHub can have on the workflow and participation. And the ZeroMQ community is completely embraces this. So for this, we have the C4 collaboration model, and that's the collective code construction contract. And C4 is actually an evolution of the GitHub fork and pool model, but then more aimed at providing the optimal circumstances for free software projects to collaborate. So, and there's even an RFC for this. Next slide. So, and C4 is formalized in RFC 42. So it's the answer to everything. C4 was is quite a change from the classical development approach. So when it was introduced, Peter later made a diagram from the Git metrics of the ZeroMQ projects, and as you can see, that the activity really increased. So the community follows this practice of C4. Yeah, we have many contributors and many projects ranging from native implementations of the ZMTP protocol to higher level patterns built with the core library. And the community has physical meetups and a hackathon at the yearly FOSDEM event in Brussels. And the community is also very RFC driven and completely self-steering. We do have actually two benevolent dictators for life. That's Luca Bukassi and Doran Somek. But yeah, I think they are there more for just in case of situations and probably the administrative sorrows. So I hope you get from this introduction that we have a very active community, but most of all, a very friendly and welcoming community. But let's get into more technical stuff. So next slide.
All right, thanks, Anna. So before we get into all the nitty-gritty details, let me quickly explain in a few words what ZeroMQ is. So ZeroMQ looks like an embedded networking library, but actually acts like a concurrency framework. It's fast enough to be the fabric for your cluster products, and it's simple enough to be used for any of your messaging needs. At the core of ZeroMQ, we have sockets, and those sockets carry atomic messages across various transports. And because sockets are being the de facto standard in API for network programming, ZeroMQ also presents a familiar socket-based API. Now we're going to look at the features of ZeroMQ, and we are starting by looking at the key difference between conventional sockets. So conventional sockets only allow limited relationships like strict one-to-one, connecting to peers, many-to-one, many clients, one server, or in some cases one-to-many, which would be a multicast scenario. ZeroMQ sockets are by default peer-to-peer, meaning you can connect sockets to multiple endpoints while simultaneously accepting incoming connections from multiple endpoints, and thus allowing many-to-many relationships. While in traditional TCP topologies, the server is the peer that binds and the client the peer that connects. ZeroMQ being peer-to-peer by default means that there's actually no distinctions between clients and servers. So both clients and servers can bind or connect. Further, ZeroMQ sockets are built around an asynchronous I/O model, which means for the user that the timing of the physical connection setup and teardown, reconnect, or effective delivery are transparently organized by ZeroMQ itself. So if the physical connection is not yet set up or due to some networking issues is currently not available, ZeroMQ will queue up that messages for you, and once the peers available, send them out in the background. So you don't have to worry about these physical connection issues. One thing that makes ZeroMQ especially tasty for developers is that it uses different socket types to implement any arbitrary messaging pattern, like fan out, publish, subscribe, task distribution, or request and reply. We'll have a look at the socket patterns in a bit. ZeroMQ sockets also provide a clean abstraction of the underlying network protocol, which hides all this complexity and also makes switching between those protocols very very easy. And on the right side of the slide, you see that we support a lot of protocols. There's INPROC, which is the ZeroMQ proprietary protocol for inter-thread communication. We have IPC for application communication, and we had the TCP and UDP. And there are some uncommon protocols also like PGM and Norm for multicasting and GSS API. And there is also WebSockets, which is quite new and which is still in draft state. And of course, ZeroMQ supports encryption and authentication, but we won't get into this in this talk. ZeroMQ has quite some language support. The main transfer protocol itself is implemented in at least C++, which is the reference implementation. There are implementations in Java, C#, and I think there are actually 2 implementations in Erlang. And then there are over 40 language bindings for either the core implementations or any higher level implementations. Now let's get into some basic concepts. And the first, before we continue to talk about sockets, we quickly look into ZeroMQ messages. So a ZeroMQ message is actually just a discrete unit of data passed between applications or components of the same application. And for ZeroMQ, the message itself is just an opaque binary data. So the simplest ZeroMQ message consists of 1 frame, which we also call message part. And a frame is simply a length specified block of data where the length can be anything from 0 upwards. And the only limitation we have is that one message must fit into memory. If you have the need to send larger messages, then you must break them into pieces and send each piece as a separate message. One essential thing is when ZeroMQ, when sending messages through ZeroMQ, ZeroMQ guarantees the delivery of to be atomically. And that means that either all frames are delivered to the recipient or none of them. And this concept allows us to send and receive a list of frames as a single on the wire message. And we can be sure that the recipient will get the whole message and never just a part. How you get your data serialized into a message is actually not a concern of the ZeroMQ protocol itself. Though some of the language APIs do provide simple serialization options, and the community even developed a simple serialization protocol which integrates nicely with our APIs. And of course, you can use any serialization protocol of your choosing, for example, protocol buffers, message pack, or JSON. Now let's talk about some socket fundamentals. So each connection out or into a socket will create its own pipe or buffer for sending and receiving. And this is illustrated here with 1 sender that is connected to 2 receivers. And we see for each receiver, the sender has a send buffer, and both the receivers have a receive buffer for the incoming connection. Now, when we can send messages rapidly from one process to another, we'll soon discover that memory is actually a really precious resource that can be trivially filled up. And all it takes is just a few seconds of delay in one process that can turn into a backlog and eventually blow up a server, unless we take precautions. So let's imagine a scenario where our sender is sending messages at a very high frequency at receiver 1, and suddenly our receiver gets very busy. This could be garbage collection, CPU overload, or anything else. And the result is, for a short period of time, we can't process messages. Now what happens is that some of our messages will sit in the receiver's receive buffer, some of them will sit in the receiver's network buffer, some will sit on the Ethernet wire itself, and some will sit in the network buffer of the sender, and the rest will accumulate in the sender's memory, and as rapidly as our sender sends them. So obviously this is bad. And if you don't take precautions, our sender could easily crash because it runs out of memory. And one solution could be to pass the problem up upstream, and because our sender is probably getting messages from somewhere else. So we tell that process to stop, and that process tells other process to stop, and so on. And this concept is called flow control. And while this sounds plausible at first, what happens if you're sending out like a Twitter feed? Do we tell the whole world to stop tweeting while our receiver gets its act together? That's very unlikely. So flow control works in some cases, but not in others. That's why ZeroMQ uses a concept of high watermarks that essentially define the capacity of its internal buffers. So when we're hitting the high watermark, like our sender in this scenario here, our sockets enter a so-called mute state. And depending on what socket type we're actually using, we'll either drop the message or block the caller, and thus preventing our buffer from overflowing and us running out of memory and eventually crashing. Now let's get into the tasty stuff, the socket patterns. And first up is the request and reply pattern. The request and reply pattern is intended for service-oriented architectures of all kinds and comes in two basic flavors, synchronous and asynchronous. And the request and reply sockets that are shown here are the synchronous sockets. And those follow a strict request-reply pattern like you have in HTTP, which means after sending a message on the request socket, it expects an answer and vice versa. And if you're trying to send a second message before receiving an answer, that will actually result in an error. ZeroMQ being able to support many-to-many connections, when we connect one request socket, like in the example below here, to multiple response sockets, then messages are routed or distributed to our services in a round-robin fashion. And the mute action for the request socket is to block. So, and the response sockets don't have a mute state because they only are reacting. To complement the synchronous sockets, ZeroMQ provides the dealer and router sockets as asynchronous counterparts, which may be mixed in various ways with the synchronous one, like you see in the diagram at the bottom. We'll later see examples where this is very useful. The dealer is the asynchronous replacement for the request and reply sockets and allows communication in arbitrary patterns back and forth. And when it's connected to multiple outgoing sockets, those are routed in a round-robin fashion. And incoming messages are fairly queued between all incoming connections. And then we have a special socket, which is the router socket, and it does exactly what its name tells. So it routes messages to a specific connected peer, which is very useful when we're looking at use cases beyond load distribution. And we'll also have an example queued up later for this. For now, we're gonna look at the next pattern, which is the publish subscribe pattern. And this pattern is intended for event and data distribution, usually from a small number of publishers to a large number of subscribers. But it also works from many publishers to just a few subscribers. So the pub socket provides one-way broadcasting to a set of subscriber, and is used mainly for transient event distribution, where the actually stability of the network is more important than the reliability of the traffic. And thus, when entering the mute state, the pub socket will not drop messages, but it will drop them to ensure consistently low memory usage. For many-to-many use cases, there are two special sockets. Those are the xpub and xsub sockets. These sockets provide some more information about who is connected, what subscription are available, and we will also see them in action in a later example. For now, I will show you how subscriptions work in ZeroMQ with the pub sub sockets. And a publisher sets a record by entering an array of bytes in the first frame. And this first frame is our topic frame. So in this case, our publisher's first frame are cities, and the further frames are just arbitrary data it can send. And in this example, it's the temperature measured in the system at the current time. In order for publishers now to subscribe to this temperature feed, it sends a subscription with a prefix filter. And this prefix filter is then applied to the first frame of the message. So here in this example, we have one subscriber that subscribes to Dallas, the second subscriber subscribes to New, and the third subscriber subscribes to New York. Now, when the publisher sends its three messages, Dallas, New York, and New York, they are prefix matched on the first frame. So the temperatures for Dallas go to the first subscriber, the temperatures for New York go to the second and the third, and the temperatures for New York go to the second subscriber, again, because they are prefix matched. Actually in ZeroMQ, it's the publisher that checks the subscriptions. So if a subscription is not matched, then the subscriber will never get the message. So this reduces the amount of messages that are sent over the network. The next pattern we're going to look at is the pipeline pattern. And the pipeline pattern is intended for task distribution, typically in a multi-stage pipeline where one or few nodes push work to many workers, and they push the results to one or few collectors. And the example you see here is a typical divide and conquer scenario where we have one ventilator that pushes out tasks to a set of workers, and who push their result into a sink. And this pattern is most reliable insofar as it will not disregard any messages unless a node disconnects unexpectedly. That's why its mute action is to block and not to drop the message. And it's scalable insofar that nodes can join at any time. The last pattern we're going to look at is the exclusive pair pattern. The pair socket is not a general purpose socket like the ones we saw before, but is instead intended for a specific use case where two peers are architecturally stable. And this usually limits the use of the pair sockets within a single process for inter-thread communication. And one typical use case of a pair socket is the actor model for concurrent computation. So by now, you're probably craving to see some code. And it's the hello example, of course. So what you're seeing in this example is an request and reply as a request client that and a reply server. And now, if we want to connect them, all we need to do is create a new socket of this reply type, bind that socket to P, and then we go into a loop and we wait to receive a string from our on our socket. When we receive it, we print it, and then we send back the string world. On our client side, we do the same vice versa. So we create a request socket. We connect that request socket to a server. And then we're gonna go into a loop for 10 times and sending the string hello to our server. And then we're expecting back a string, which we print on the console. Second. Okay. Now we're gonna get into some more challenging parallel and distributed patterns. And in the real world, our society and economy is usually filled with intermediaries and who have no other real function than to reduce the complexity and scaling costs of larger networks. And real-world intermediaries are, for example, wholesalers, distributors, managers, and so on. And while ZeroMQ aims for decentralized intelligence, that doesn't mean that our network is an empty space in the middle. As in the real world, it's usually filled with message-aware infrastructure, and ZeroMQ enables us to build that infrastructure. And the concept of message-aware infrastructure in the middle is called intermediation. And in ZeroMQ, we call these, depending on the context, proxies, queues, forwarders, or brokers. And because intermediation is an extremely common, we look into a few problems that can be solved using an intermediary or proxy. Now, the first that comes to mind is dynamic discovery. When we're designing distributed systems, discovery is probably the first thing that's going to hit us. It's especially difficult when pieces in our network may come and go as they like. And yeah, this is what we call the dynamic discovery problem. And there are several solutions to dynamic discovery. The simple solution is entirely avoid it. Just hard code your everything or have it in your configuration by hand. Which means when you add a new piece, you reconfigure your entire network. In practice, though, this leads to an increasingly fragile and unwieldy architecture. Let's take the example on the slide. Here we have one publisher and 3 subscribers. We can easily connect the subscribers to the publisher and even add subscribers as we go. That's easy. But if we add more subscribers, suddenly it's not so easy anymore, because now we need to reconfigure our entire network. And if you continue to connect each subscriber to each subscriber by hand, the cost of avoiding dynamic discovery gets really high. There are a lot of options to solve this problem, but really the simplest answer is to add an intermediary. That intermediary being a static point in our network to which all other nodes connect. And in the click messaging, this is the job of a message broker. Now, ZeroMQ doesn't come with a message broker, but we can easily build a similar intermediary. Now, in this example, you see that we connect all our publishers to an X sub socket. Then we have some proxy logic in the middle, and we forward the pub messages to the X pub socket, which is connected to all our actual subscribers. And thereby, we're solving the dynamic discovery problem. So we can add publishers and add subscribers without needing to reconfigure our whole network. And because this is such a common pattern, ZeroMQ actually has built-in support for this. And all we have to do is create two sockets. Now our front-end socket, the X sub socket, a back-end socket, the X pub socket. And then we just bind those sockets to TCP ports, for example. And then we just call the ZeroMQ proxy functions and give it the front-end and back-end sockets. And then ZeroMQ does its magic and solves that issue of the forwarder for us. Another great example of the forwarder pattern is actually the transport bridge, which allows us to connect an internal network to an external one. Now let's look at another intermediary, which is the shared queue. We have already seen how request distribution work using request reply sockets. And as you see, this architecture has the same downside as the pub sub we just came from. And to solve this problem, we're going to introduce a request and reply broker in the middle, which is again the static node in our architecture. And this broker will fairly route requests from our client to our services and send back the reply to the correct client. Again, this request reply broker makes our client server architecture easier to scale because clients don't see workers and workers don't see clients. And of course, it's again very simple to add such a broker in ZeroMQ. Again, create a front end and backend socket of again this time types ZeroMQ router and ZeroMQ dealer, bind them to a TCP socket, and just call it ZeroMQ proxy. There are quite a few patterns like this. For example, heartbeating, robust, reliable queuing, high-speed subscribers, reliable pub sub, or large-scale file publish, which you can all read up in the C guide at cguide.zeromq.org. But because the time is limited, we are not able to get into all of them now. Now we are going to look in a few libraries built with ZeroMQ that occupy that empty space in our network architecture and enable us to do nice stuff with distributed computing.
You need to unmute Arno, I think.
Yeah.
Sorry, is this better?
Yes.
Yes.
I was afraid I was going to make that mistake. But okay, Zaire is a ZeroMQ project for local real-time peer-to-peer group messaging. It's a C library with a very simple API of whispering and shouting messages. Being simple, it requires no administration. Peers may leave and join at any time, and it requires no broker. Peers can directly talk to each other. We call this whispering, or they can talk to a group of peers. We call this shouting. It's fast, low latency, and it's also designed for use on Wi-Fi networks. I used Zaire a lot in my projects for code orchestration. So like having a computer orchestra. For example, we also created to you a multiplayer piano. So everybody could join in and play piano with MIDI devices. And it also kind of illustrates the latency because that worked really perfect. Yeah, it has an RFC number. It's number 36. The protocol is called ZRE, ZeroMQ Real-Time Exchange Protocol. Discovery is done using broadcast or multicast, IPv6. Or if it's not available, you can also use a gossip model for discovery. Yeah, internally it uses the parents Kevin was talking about. It uses the exclusive pair for controlling threads and the router dealer sockets for the communications between all the nodes or the peers, and a DGRAM, a UDP socket for the discovery. And typical use cases are yeah, local service discovery, clustering a set of services, Internet of Things kind of stuff, controlling a network of smart devices, multi-user applications. Next slide, we have a little code example. This is just a very basic node from Zaire. You just define, you give it a name, and it joins the group room, and then shouts in the room, hello, my name is, and it prints whatever message it receives. Of course, this is a very simple example. In a bigger application, you should poll for sockets instead of waiting for a blocking receive. Yeah, and you also, to run this, you have to run multiple instances to see how they interact. And it doesn't matter if you run it on a single host or on multiple hosts, as long as they can see each other on the network, they're fine. So, yeah, Dafka, that's you, Kevin.
Yeah, so Dafka is a decentralized distributed streaming platform, which was actually built during one of our FOSDEM hackathons. And it's designed to provide robust and reliable publish-subscribe, because the ZeroMQ publish and subscribe socket itself are not designed for being robust and reliable. It's peer-to-peer, meaning publishers can directly talk to subscribers. It's fault tolerant by storing messages persistently on demand. And it has a very simple protocol, which is simple enough to be implemented during a one-day ZeroMQ workshop, which I actually held in the past. And this protocol makes a nice use case in implementing when getting to know ZeroMQ. And of course, there's an RFC. It's RFC 46. And
We'd like to go to questions in about 2 minutes.
All right.
Yeah.
Now, if is there any relationship to a phonetically similar sounding streaming product? Yes, there is. Dafka follows a similar concept for topics, partitions, and records. And I quickly go over these slides. So Dafka topic consists of multiple partitions, where each partition is fed by a single publisher. Consumers track their own offset in the partitions, so they might come and go as they like and pick up where they left off. There are 4 types of players in Dafka. They're producers who publish records to a single partition, so consumers who subscribe to one or more topic. There are stores who store records on partitions and republish them on demand. And we have towers, and towers are act as intermediaries, like the one we saw earlier, but we only use them for discovery and not for sending messages. Now, how does producing and storing messages work? As I mentioned earlier, Dafka is a peer-to-peer protocol, which creates a many-to-many relationship between producers, stores, and consumers, which all have a pub socket to send and sub socket to receive messages. And because of its peer-to-peer nature, messages produced are simultaneously sent to both our stores and consumers. And whenever a consumer finds out that it missed some records, then it goes and fetches the messages from either a store or a producer, and those send then the missed messages directly to our consumer. Yeah, that's Dafka in brief.
Yes, Vector is the research project I'm currently working on. And then quickly a little bit of background tech, because there's a situation we have a lot of students in the art academy that want to use computer technology, and please understand they are not computer science students, but they do want to use all this technology. But yeah, we teach them lots of tools, but the basic problem is these tools don't use all the cores in the computer. So the question I have to deal with is how can I provide them with a tool or a mental model or programming lessons that can also embrace using multiple cores in the computer. So that's the Swactor project. Next slide, Kevin. So it's a hybrid text-based and visual-based programming environment. It uses the actor model for concurrent programming, and it's built using ZeroMQ technologies, mostly ZActor from ZeroMQ. It kind of begs to have Xia merged into it, so we can also work on the network. You can create actors using C or C++, but also in Python because it embeds Python. It's still in a research phase, and we're specifically designing for concurrent programming suitable for novice users. But I'd like to use it myself as well. So I hope to keep it useful for experts as well. Yeah, so the screenshot you can see here is the visual editor, basically a node editor where you can edit the actors and manipulate them. Internally, again, it uses exclusive pairs and mostly the pub-sub pattern between all the actors. And yeah, and all the examples that we've been showing. Oh, and next slide, Kevin.
Yeah, so there's one little project we like to highlight for you. It's just ZeroMQ, the high-level C binding, which wraps the core API in a semantic way that leads to shorter and more readable application. And it also hides the differences between ZeroMQ versions. And if you're working with C, this is the library you want to use to get started with ZeroMQ, because it provides things like the actor model, event loops, discovery, and even easy access to security.
So yeah, that was already asked in the chat. So what's the roadmap? So basically, the answer is there is not really a roadmap, because, well, the community is self-steering. So there's no roadmap laid out. People need features and they start building it. And that's how it gets introduced into ZeroMQ, usually by a process of first in the draft state, and then once it stabilizes, it's marked as stable. And it's important to know that we find it very important to not break APIs and not break ABIs. And we put quite a lot of effort into protecting this. So it's quite an organic process. We cannot say this is really the roadmap for the coming years. What is happening now is the new socket types, thread-safe sockets, and like mentioned before, WebSocket transports. That's the biggest thing that's being changed or worked on now, and they are already there in draft state. Yeah, I think we have to conclude talk then and then go over to the questions.
So Richard, you want to guide the questions?
Yes. Okay, so we got a few here queued up from Tucker and I. If anyone else has any questions, please throw them into the chat, into the Zoom chat. So the first up is can ZeroMQ sockets be used from lightweight threads, kind of like OpenMP tasks? And I think you kind of went into this a bit. There seems to be a protocol for doing this. I won't answer for you.
Kevin, we have these pair sockets, which are specially designed for enabling communication between threads. With the current sockets, we do have a problem that they're not thread safe, because we're sending multiple frames, and each frame is a call to the library, we don't know which thread will then conclude or start a message. So with the new socket types, which will only support one frame, they are also thread safe. But you could, so if you're sending messages between your threads, then you can use the pair sockets and use, for example, an actor model.
Yeah. So I think also the most important thing is that this is quite a lot of discussion always, is that you cannot share, or you shouldn't share, sockets with threads, so that multiple threads use the same socket. You can, if you know how, but basically this is also a discussion of which paradigm are you using to program. So yeah, it is possible, but yeah, the thread safe sockets are specifically designed to be able to do that.
This is a great point. Typically, you would have a socket per thread in sockets programming, anyways. But then again, you're doing message passing. You might want to say, well, I want to send a message to this particular, socket pipeline. It sort of makes sense. It's interesting intersection there.
I'm currently working. Yeah.
I was just going to say the reason behind the question is, if you're using lightweight threads, or what OpenMP would call tasks, you don't actually know necessarily what heavyweight thread you're using. Yeah. So, it might bounce around between different heavyweight threads. And I'm just curious whether lightweight threads have been considered at all. It sounds like not yet, but I've been trying to use OpenMP and ZeroMQ together, and it's been a little bit of a delicate dance. And I was curious whether you
have you been using the new sockets or the existing sockets?
I don't know. I've been using Zyre. I've been using Zyre. So
yeah, those are not the new sockets, indeed.
Okay.
So this one from me, it's and you did kind of touch on this a bit, but I'm curious about what error handling looks like. So I mean, I know you've got blocking. We roll back a bit. So the question is really about, like, if you've got a node that's sending or receiving messages, and it becomes isolated from the network for whatever reason, how can you find out about that happening? And I know you've got blocking is one way if you're sending, and then you're starting to block, and I presume you can time out. But if you are using muting, is there a way you can look into the status of the library in the back and say, how's it looking back there?
Yeah. Okay. So while ZeroMQ takes care of this in the background, there's also an option how we can monitor the current state of the connection. And this is achieved by opening a socket to the core library, and then the core library will send messages to you, which informs you about the state. So whether the connection is still open, it's connected, it got disconnected, or any protocol specific state that you can get it out of ZeroMQ. Yes.
That's interesting. And can that connection be kind of proactive, so to like send you a message when it says, "Hey, I lost connection," or do you have to actually pull it?
Well, you have to read the socket that tells you that the connection died. So.
Okay, and so we have, and I think this question was a bit before, as you went over this, as a roadmap of, what's the roadmap ZeroMQ and for Zyre. I don't,
Yeah,
I mean, you mentioned there's no real roadmap for ZeroMQ, but how about Zyre?
Well, for Sire, we're currently testing in draft mode an election algorithm. So if you have draft mode enabled, you can actually, for each group in Sire, you can elect a leader. So that's one of the new big features.
Neat. Okay, and so this is kind of the last one here is, so does ZeroMQ support scatter gather paradigms or similar low copy, no copy capabilities? Is that something that's maybe coming?
Yes, there's actually a new pair of sockets called scatter gather.
Nice.
They're similar to the publish subscribe sockets, and in ZeroMQ, if you use the inproc protocol, it's for inter-thread communication, it's always 0 copy. And if you're sending over the network like TCP, ZeroMQ does it best to avoid any copies. So I'm not the expert for that part of the library, but during the hackathons, there's always a huge discussion on how to further optimize this.
Yes.
Yeah. There are also some options for zero copy messaging, like doesn't do any copying, but it's very specific. It is in libzmq. I've never used it, but I know it's there. And
okay, well, I want to thank the
can I
speakers.
quickly
Oh,
Mark?
sorry.
Because there was a comment like, so currently ZMQ is not thread safe, and that's kind of delicate, because so I have to respond quickly, is that yes, ZeroMQ is thread safe. The context you create to use ZeroMQ is thread safe. Only the classical sockets are not thread safe. The new sockets in draft state, they are thread safe.
Sorry, I didn't ask that one because I did feel that you kind of answered that.
Oh, okay.
So,
I don't know who's seeing all these questions, so
no, thank you for clarifying.
So ZeroMQ can be thread safe if you restrict yourself to only sending one frame for a message. So then it's thread safe. If you use multiple frames per message, then that's no longer working.
But it seems it's clearly in the roadmap, and it's something that I think is in the pipeline for sure, and even in beta already.
Yes.
Okay, so we only have 3 minutes left in our break. So at least for Richard, he has to give a talk in 3 minutes. So I want to thank you very much. It was very interesting, certainly for those of us who have started playing with distributed computing. ZeroMQ sounds like maybe a real simplifying approach. And I'm personally very interested in distributed computing programming languages, and plan to embed Zyre at least, but ZeroMQ more generally as part of that language. So I'll talk more about that in the panel session. But so you can all now spend 3 minutes getting your coffee, and Richard will take over in a few minutes with his talk. Thank you very much again.
All right.
Thanks for having us.
Thank you. Awesome talk, guys.
Okay, it looks like Richard is back. And how many of you managed to get a cup of coffee in 3 minutes? We'll see. But our next talk is by our co-chair, Richard Y., who is the founder and managing director of Annexi Strayline. And I'll let him explain the secret sauce behind that name. I've never quite remembered it myself. It's a startup focused on the practical application of proven high integrity technologies to mainstream software, particularly in large scale cloud and IoT applications. Richard's an evangelist for the safety and maintainability provided by the Ada language. There's Ada. Thank you to our sponsors, Sigada. And is a member of the ISO Ada Rapporteur group, which we call the Ada Rap group, for those of you who are, it's a standardization committee that has been shepherding Ada through its various versions for the last many years. And it's generally tasked with the ongoing development of Ada. Ada 22X, which has been mentioned several times, is a product of the Ada Rapporteur group. And Richard is a relatively new member compared to some who've been on it forever, but he's been very valuable providing an outside of the compiler vendor world where many of the ARG members come from. Richard holds an honors Bachelor of Architecture with distinction from the University of Toronto. So Richard, I'll let you take it away.
Thank you. Thank you for the great introduction. Okay, let me share my screen. Okay, how's that look?
Looks good.
Okay, awesome. So a lot to unpack. Forgive me if I talk a little fast here. When I tried to put my notes together for this presentation, I started pouring my heart out, and I had to kind of. So I gotta rein myself in. I'm very passionate about a lot of these topics. So let's first begin. Let's clear the air a bit with what's with all these crazy names. You know, Annexi Strayline and Xeris Apex. So Annexi Strayline is we focus in as Tuck introduced, you know, in bringing Ada really into mainstream software and particularly in cloud and IoT. And we do also consulting, training, development, these kind of things. And we're really on a large scale, we're about promoting a more mature, stable approach to software. And we also are really dedicated to developing and maintaining a high quality open source Ada components, because there is kind of a lack of that out there. And particularly we look at, using licenses like BSD license, so that it's truly open and source and usable. So we've got a lot of that kind of under development now. So actually the name itself originally, and it's something that I'd spent a long time thinking about, and it's really what we were meant to be originally is more of a holding company, because there's a lot of, I think, potential ideas that I want to develop as probably a aspiring serial entrepreneur, I suppose, something like that. And so I just wanted a name that first started with an A, that was distinctive, that was very generic, that did not have any specific sort of role behind it. And so, think of it as something like Berkshire Hathaway, but with a lot less Warren Buffett. I could spend too much on there. So now let's look at Xeris. Oh, sorry. I want to go back in here. I'm getting a little too excited, but I think specifically is that we're kind of our own startup incubator. So, and I'll talk about this a bit later, but we're looking at building some products that, with these kind of technologies that we're building, that'll be kind of their own thing. But Annexi Strayline is about trying to bring as much of that technology that we can open source as possible, and have that kind of be on a free license. So Xeris has actually got quite a long history for it. I'm going to try to get through this really fast, but and also to kind of anneal my own acute imposter syndrome in this group. So although I don't have a degree in computer science, I started when I was quite young. And so here in 1999, this is the first language that I designed, called Qtran. It actually stands for translator into quick basic. But I was trying to develop a language that was graphically oriented so that I could move on to develop something that I was also very interested at the time, which was operating systems and user interfaces, these kind of things. And so this is what my first attempt looked like back then. So I was only 12 at the time. So forgive me for, you know, it might not be the most pleasant to look at, but it was running in DOS. So, you know, so there was this time around the same time where I was in my dentist's office, and the secretary there had restarted their central system, and I saw this screen. And it said, this is SCO Xenix System 5. I had no idea what that was, but it sounded so cool. It was like, that's so exotic. So, I mean, I really, at that time, I was really interested in operating system development. And this is where I really wanted to kind of head in the next kind of challenge in my journey here of kind of self-teaching back in those days when it was a little bit harder than it is now. So I actually talked to a bit of a mentor at the time who was a bit more ahead of me. And, you know, I was telling him about my ambitions and how I was going to write this operating system using, you know, BASIC. And he said, whoa, wait, you know, you're going to need something a little more low level than that. So that's when I started to learn C. But I embarked on this project in the year 2000 to create this operating system called ZeroMQ. So this is where the name comes from. And, you know, I had a mailing list and everything. This website, I installed, you know, Netscape in a virtual machine to get this, just to keep it authentic. But this is the actual web page from the 2000s. I blurred it out because it's embarrassing. So fast forward, you know, 16 years later, it actually happened. So I had a first boot of what was then ZeroMQ. And this is a whole other project that I can't really talk about today, but it was kind of used all the skills that I had put together. So it was pretty fun. It ran at about 20 kilobytes on a AVR microcontroller. So it's fully multitasking and all these kind of things. So that was neat. But around the same time, I actually, this is when I came in to learn about Ada the first time. And I don't have enough time to go on that story, but I'm a huge aviation nerd, and I found out one way or another that the Boeing 777 was all in Ada, and I thought, what's that? And I went to kind of find more about this language, and it really blew my mind because it was, and I'll get into this in a bit, but it really, to me, was the answer to the question of like, what, you know, the software community had some certain issues with its quality and some of the practices towards developing large projects that I thought was kind of problematic, and I really felt like Ada was addressing these. So I wrote this first one in C, and clearly that's a problem when you get really interested in Ada, because then, you know, you want it to be in Ada. So we'll get to that in a bit. So this leads nicely, and I give this introduction because I think this background says a lot about, you know, why I made certain decisions that I'll get into. So I'm going to kind of play back on this later. But, you know, the first one is like, why did this take so long? So the 16-year gap, I wasn't working on it for the full 16 years. When I got into high school, it kind of diverged a little bit. Things were a little bit different back then. Computer science wasn't as mainstream as it is now, which is nice that it's been changing. But back then it was a bit of a, you know, I didn't quite see my life being that way. So I went into architecture, and, you know, I graduated from university with a degree in that field. And I think actually this was a huge, it was a great decision, because the thing is, so, you know, what I always loved about programming from the very beginning is the ability to build really, to build real things with nearly no practical limitation. You know, you can really dream as far as your imagination will allow you, and only the only real limitation is the true material cost is your time. You know, software is one of the purest forms of creation I know. The tools are dirt cheap, and the materials are plentiful and infinitely reusable, right? Memory and processing. Once you have it, you can kind of do whatever you want with it. And with software, you can build real things that impact real lives, and you can make fantastically intricate systems that appears magic to the average user, all without moving mountains and without $1 million or even a permit. So, you know, actual architecture is nothing like that, but it teaches us some very important lessons that I strongly believe the software industry could use, could benefit from. And you know, the heart of any architectural design is designing for humanity. And our architecture also teaches us about designing for construction. And by designing for construction, I don't mean in the literal sense. I mean in the structured process of understanding the problem and then understanding the solution, right? So it's a deliberate process about setting and working within certain limitations. It's a process about applying human strengths to human problems. And actually, humans are excellent at designing things. We're really excellent at using structure, organizing function. We're not excellent at repetitive tasks, at getting boilerplate correct every time. And honestly, we can be pretty bad at minute details. So it's important that we have the right tools and approaches to facilitate designing software with this kind of a mindset. And so this kind of leads me into, you know, responsible language selection. There's some basic truths that I think are maybe not recognized. And first is, you know, is it hard to learn as a language? Is a language hard to learn? No, I mean, really, most languages that are actually practical use, any decent programmer is going to be able to learn it. So that should not be a question when you're deciding a language, in, you know, our opinion. So the must-haves you've got are
7 minutes before question time.
Well, that was really quick. Okay, so we want to have direct language support for design, programming at large. You know, you want it to be horrible for hacking because, well, hacking is horrible. You want to have good abstraction, encapsulation, typing, all these kind of things. And I'm going to have to run through this, obviously, because I'm a little bit behind. But I think, you know, Ada is the obvious choice. It offers these things. We have these basic advantages that are often talked about with Ada, which is these data modeling type systems. You're not using, you know, everything is integer 32 or 64. You're actually talking about values. It's got this progressive design with concurrency that's been there since the start in distributed computing. And, you know, it's about specifying things first, about, you know, explaining the language first. So what you're trying to do first. And yeah, I'm just going to have to jump through those quickly. So finally, we get to the problem. And the problem is, so what we're dealing with, so Tame is actually a subsidiary company of an Straight Line Network. It's a startup that we're building. See, it's probably the first startup that I'm aware of in the mainstream that's actually using Ada. So we're pretty excited about that. And it's basically an app that prioritizes tasks in real time. It's inspired by the F-22, which is also written in Ada, which uses sensor fusion techniques to do largely the same thing. This is an actual not classified diagram of sort of how this system is together. So when you're approaching certain systems like this, the traditional model you'll use is microservices model, right? And so microservices, the issue is you've got a bunch of these separate programs, often on separate machines or containerized, that are communicating with each other with JSON over HTTP. It's very heavyweight, and it can be very difficult to sort of reason about, and it can be heterogeneous to a point of really working against you. A lot of fragile interactions. Dynamic scaling is very complicated, oftentimes. So what we wanted to do is we're using this kind of idea of a microservice where you're splitting out things into certain roles, into specific roles that you're trying to, and I'm trying to think ahead here. I'm going to squeeze all this in. But this is where I came back to Xeris, and it's like, what are we going to really make this into? And so we want to have an extremely scalable concurrent communications system. And this plays well with what we talked about with ZeroMQ before. And that works with an optional exokernel. And this is very Ada specific. So our goals really about ease of use, stable interface, and a superior architecture. So Xera's Apex is really structured in 3 layers. So you've got a grid, which is a shared memory region associated with the user-defined type and some specific capacity. So each grid can be associated with any number of tracks. And a track is basically a queue dealing with these units. And a theater is a set of processing memory resources, or a NUMA region, for example, that autonomously operates with a collection of partitions which are communicating over these grids of tracks. And so the tier horizon is really a collection of these theaters that can see each other. So they can all operate on the same tracks and the same grids. So again, a track is a concurrent lock-free queue or a single item stack. And this is for a pub sub model, and I'll get into that in a second. So each track is 128-bit ID, so you can have tons of them, and the grids have an 128 ID. So we have 2 types of tracks. A commission track is for atomic message passing, and distribution tracks are for your pub sub model. So the logical architecture is a bit like this. So you've got in each theater, which has a physical piece of memory, you have any number of these grids, which are essentially logical arrays of your units of data. So these are some kind of a type that you've defined. We'll get into that in a bit. And then you have tracks which queue these units, and then you have these theaters which can directly interact with these tracks across your larger region, which is known as a tier horizon. And this can be moderated through the Marshal, which is just its own partition that looks at coordinating these kind of movements of data between theaters and discovery and all this kind of stuff. And then you've got, so there's 2 ways you can deploy this. Either you can host it on FreeBSD or Linux, and you've got all the facilities you're used to. And then we have the exokernel, which is really for bare metal development. Initially, we're targeting ARM and RISC-V, but this is for having, really secure enclaves, bare metal performance for the edge and IoT. It's got a native ADA Annex D, real-time scheduler, so it works with all those kind of ADA semantics. And so the user interface is where we want to be really easy. When we say user, we mean the ADA programmer. So the tier horizon interface is a simple set of generic packages that you instantiate based on the type that the type is your message, right? So when you want to set up a grid, you provide your type, you instantiate this package, and then you can operate on it by creating tracks and then communicating them over them through these operations. Again, you have 2 types of tracks: commission track for atomic message passing and distribution track for kind of a pub sub model. So the commissioned track, quite simple. You pull off a item from the grid that's not being used, and you gain ownership. And then you can schedule that to be dispatched onto a specific track. And then you can keep commissioning off of a track, taking units and taking ownership. So here's an example, kind of a typical example I've got. So if you've got a grid here, we're just calling a service grid. You've got a work item, which is your unit on the grid. You can commission it off a track. So it's like pulling it off of a queue. And then you can do something with it. And then you can redirect it optionally to another track after you've processed it or whatever. And then once it goes out of scope, ADA finalization will take over and will put this back onto the appropriate track so that another partition anywhere else in the tier horizon can then dequeue that and do what it has to do. For a distributed unit, there's some kind of more interesting things you can do, such as fan out. But basically what you have is you take a unit and you distribute it onto the distribution track with some kind of a release generation. So the generation is it's a 128-bit monotonically increasing number. And basically when you try to put a new distributed unit onto a distribution track, it'll only get pushed onto that track if it has a higher generation at the time. And so this will
to wrap up, Richard,
Yep.
so we can go to questions.
And I am almost there. Yep. So what this allows you to do is to actually have publishers distributed in your system. So you don't have a single publisher. You can have multiple publishers So you can have some high availability there. And so we've got an example here where we can also use, say, the Ada parallel features to fan out things, to fan out distribution units. And so, I mean, I had a bit on the implementation, probably not important. Sorry, guys, I kind of tripped over myself. It was it was a bit more than I really had time for. It's a lot to unpack.
So do you want to reach a conclusion here?
That basically is my conclusion. So essentially, this is something we're working on that we're using internally right now, but we are going to open source this to the broader community. And essentially what this really comes down to is we're creating a RDMA focused distributed message passing model that's very Ada specific. It gets to leverage the safety and security features of Ada and the type checking of Ada to act as a basis, as a foundation for kind of a larger architecture of a large distributed system. And that's what we'll be using it for. So I should go to my Q&A slide, but you know, we will be updating on this through our blog. So there's the link to it. Please check it out.
So I think a critical question for some of us is, you've used a lot of terms, but not a lot of examples. So can you give concrete examples for what might be a grid, what might be a track, and what might be a theater? Because I think for a lot of people, that kind of vocabulary is not necessarily intuitive.
Yes, and fair enough. And that was what I wanted to do, but I took a little too much time. So the idea is that we believe that you know, RDMA and shared memory is really kind of the future of, I would say, not just inter-process communication, but even distributed computing. So the idea is that you've got some kind of heterogeneous set of machines that have some amount of memory, and it might be uniform, might be non-uniform, but you've got a section of memory that's connected to a set of processors that can access very quickly. And
try to talk about concrete things for people. That is like, is this give me a very specific example. Don't talk about the infrastructure, talk about the data that's moving around.
Right, so think of a theater as a machine that you're operating on. So that's typically what it'll be. It'll just be a single machine. That's your theater. The grids are instantiations of a generic package with a type that you've provided, right? And so on every, sorry?
Such as?
Such as your message. So if you're trying to communicate between, so if you're talking like on a microservices model, you've got some kind of a request that you're sending out and you need to get a response. So that request, you know, instead of being a JSON blob, it could just be a record that you want to put all your information in. And so you would have an Ada record type, and you would use that to instantiate a unit as a grid. And in your other partitions, you have the same types that you instantiate, and then it creates these two grids that'll have the same ID, and they will also verify their geometry, sizes of the type, and everything. They're going to talk to each other. And so those units are your types that are in a conceptual array, and you set the capacity. And then the tracks are what queues these units in some kind of meaningful way to you. So these are your queues, and you can have any number of these that you will set up as part of your architecture. You'll have, you know, some kind of, for example, if you had a specific service in certain partition, you would just have your inbound, your request queue, and then your response queue. And those would be tracks, separate tracks, right? And so you would take in a unit off of one of those tracks, you would do your thing, and then you would send your response back out onto the other track.
Okay. Well, I think we're going to have to cut you off here. I'm sorry. And stick around in the, there'll be another break at noon, and you can ask further questions at that time. But thank you very much. And we will now, if you can unshare the screen, we'll let Brian share his. So let me first actually sneak in here before we go to Brian. I'm going to introduce him. Boop. There you go. Let's see. So our next talk is from Brian Kleinke of Leidos USA. Challenges and lessons learned introducing Fuse, an evolving open source, I might say Java-based open source technology, into an established legacy Ada and C++ program. Brian's a solution architect at Leidos. Brian has worked on the FAA en route automation modernization program, ERAM, for 15 plus years. We have probably all flown on planes that have been very affected by this upgrade that's actually been, I think, considered a real success in the FAA's attempt to upgrade our air traffic control system. There were a lot of fits and starts in the beginning, but ERAM has proved to be, I think, a real success story. Currently, Brian is ERAM Chief Software Architect, and he holds a Master's of Computer Science. So take it away, Brian.
Thank you. Let me, the share button moved. Share my screen.
So Brian's going to focus on the problem domain as opposed to necessarily the solution domain, I think. And anyway.
Okay, you can see my screen now, right? Yep. Okay, you can hear me and see my screen, right? Okay, good. So welcome to Challenges and Lessons Learned, introducing an evolving open source technology into an established legacy Ada and C++ program. You kind of got a lot of the information from my About Me slide in the introduction, but a few things I'll mention is outside of work, I really enjoy to travel. I like to do photography. All of the pictures of various animals you're going to see were taken by myself, with the exception of this picture with some penguins. Since I'm in it, my wife took it. And I really enjoy aging wine. I have over 300 bottles of wine in a wine cellar at my house. But that's enough about me. Let's go on. So here's the agenda, some of the main topics, kind of a roadmap. It's a short enough talk, so I'm just kind of going to skip over this. So first, let's delve into the background. ERAM is the computer system that the FAA uses at its high altitude en route centers and is considered the backbone of the nation's airspace system. The system processes flight and surveillance data, provides communication, and generates display data to air traffic controllers. ERAM has an increased flexibility in routing around congestions, bad weather, and other airspace restrictions. It provides core functionality for air traffic controllers and supports satellite-based systems such as automatic dependent surveillance broadcast, EDSB, and data communications, and is operational at 20 air route traffic control centers, also known as en route centers, throughout the United States and at the FAA Academy in Oklahoma City, Oklahoma. The system-wide information management was launched in 2008, and all Segment 1 SWIM projects were required to use Fuse. So what Fuse itself is a packaged Apache system, which you can find these Apache products and use in a truly free version, but with Fuse, you're getting a support contract, and this contract is actually required if you use Fuse. And ESAS is just one part of SWIM Segment 1, and its goal, basically its purpose for existence, is to receive traffic flow messages and pass them into ERAM. So here's a picture trying to describe what SWIM is from the thousandth foot level. Provide some background, and it's not the main focus of the presentation, but walking through the layers, at the top, you'll see that there's applications. And basically we're showing that there are many different applications serving different areas of the national airspace. And the second layer is standards. And by standardizing them, it really helps with the interoperability. And third, you have managing infrastructure, but I don't work with this since we're at the top level with ERAM. And at the bottom, you see we have an IP backbone, which is how all this message is communicated back and forth, and that's through FTI. Okay, so development challenges. ERAM is predominantly written in C++ and Ada. Less than 1% of the code base is Java, and only a subset of the overall ERAM team knows Java, and an even smaller subset knows Fuse. But how is Java different? Well, in this context, for what we're doing with Fuse, there are more than one middleware options. And in SWIM Segment 2, they removed the requirement to use Fuse. So you didn't have to stick with Fuse anymore, and other Segment 1 teams moved off of it. So when we had the chance, we looked into switching to WebLogic, but it's an even heavier weight solution and require more than an overhaul than sticking with Fuse, so we chose to stick with Fuse. And how does ESAS with Fuse compare to ERAM? ERAM uses something we call Flight Deck. It's a custom middleware platform designed for near real-time applications. On the Java side, we have an Open Services Gateway initiative, an OSGI container, which is the basis for ESAS with JBoss Fuse 6.1. These are loaded in the Java virtual machine and do not directly talk to other Flight Deck applications without specific code written to communicate between the two. ESAS's solution uses a Java management bean that is accessed by a code running outside of ESAS, which talks to the ERAM monitor and control function. C++ and Ada have had best standards defined for over a decade, but it took time to adapt internal standards for Java. ERAM formal documentation has to be compliant to decentralized identifiers DoD standards, but ESAS chose a slightly different format, and it's basically a Java site report. An effort had to be taken to get that approved. So just things were a little bit different, kind of like how the baby penguin looks a little different than the adult penguins. But then we want to talk about external forces. For Fuse early on, initial development, we were required to use Fuse. The feature set was not complete as Fuse was in active development. This led to replans within the ESAS and ERAM development cycles. Skill set differences. A good C++ programmer, C++ or Ada programmer is not the same as an XML Java programmer. And with skills popular in the industry, the attrition rate was higher for our ESAS team than for ERAM's areas with more traditional languages. And then the big unexpected stimuli, which is where my picture comes from. Red Hat acquired Fuse. In about 2010, I think Red Hat bought Fuse. And basically this required mitigation in order to maintain support because Fuse 4 would end of life in 2012. In the evaluation of options to determine a replacement, that's why we had the excuse to go look at WebLogic, well, we considered it, but we chose to go to JBoss Fuse 6.1, which was Red Hat's product. And because of this, with now being under Red Hat, the support agreement changed. And I'm going to read directly a quote from the JBoss website. A Red Hat subscription is required for each and every instance of or installation in whole or in part of a JBoss product being used in your environment. This had a dramatic impact because on ERAM, we produced one image. Back then, we had one image that you could put on any box, and the box would correctly configure itself from that software. But the support agreement meant that you couldn't put Fuse or ESAS on every single box because now you'd have to pay Red Hat for every single box you have in the entire system for this massive distributed system. So we had to make it so we could split out ESAS to be on an image that was only used on the specific machines that had to be able to run ESAS and therefore Fuse. And because the ERAM system is spread out, it's such a wide distributed system at 20 different sites plus many different testing facilities, that was a big problem we had to deal with. And then every single year as part of the support contract, you have to provide a number of machines that contain Fuse and the core count for each of those machines in order to provide the cost for the licensing. And counting all these different machines that had Fuse was a kind of a big pain. So some maintenance challenges, which I kind of mentioned a little bit, Java skills versus Ada and C++ skills. Well, because we didn't have a whole lot of people that knew Java when we started doing ESAS and Swim Segment 1, we hired outside subject matter experts. But as soon as this project was finished, they left. And as most of you probably know, C++ and Java share some syntax, but beyond that, it's actually quite different. And Fuse brings in a lot of frameworks that bring Java further away from C++ development. This makes it difficult to quickly pick up a complex Fuse Java project like ESAS. There is some time required to bring a new person up to speed. Someone who is very good at this Java ecosystem may not want to work in an Ada C++ world or vice versa. And planning ahead is key. Features change, features get moved or replaced. Sometimes tech changes out for another. This can lead to a massive rewriting of code if you bet on the wrong tech. We learned that Blueprint is replacing Spring in a later version of JBoss Fuse. And then, I don't know how many of you use WSDLs, but I think WSDLs are great. Basically, if you've worked on an interface with an external system, you want to plan out that interface really, really well. In the Java world, it's a web service definition language. That's what a WSDL is. It's a document defined in XML, and it provides a well-defined contract for a service. But the beauty of these WSDL XML files is if you use Apache CXF, which is what Fuse uses, you can basically provide your WSDL to Apache CXF, and it'll provide a server using that right for you. And it verifies all the message coming in. And that was important for us because ERAM is interfacing with the traffic flow unit, which is outside of ERAM. And then dealing with end of life. In the Ada C++ world, we are used to systems running for a long time without needing to be updated. But in some worlds, like the JBoss Fuse ecosystem, Fuse products do go end of life. And because it's tied to a support contract, you're forced to step up. Basically, they won't give you support anymore. So it's kind of a complex political problem of what do you do when you're at the end of life. Testing and performance. Java comes with JUnit, and it's actually quite powerful, and it's easy to test, and it basically is free because it's there. And you can get similar systems to C++ and Ada, but C++ and Ada are compiled to an executable, which has their own advantages. Java is compiled to bytecode and uses an interpreter. And because of this, Java has a head start when it comes to building a really nice testing framework. And this is great when combining other Java technologies like Jenkins Continuous Integration Application, which builds the Java project and runs all the tests. And then we use a tool called Clover, which would verify test coverage. And this Java virtual machine is quite a bit different because it's a kind of a black box running your Java code. We noticed CPU spikes that we basically determined were garbage collection. But because ESAS is so simple, it's not that big a deal. But if you're developing a big system using Java, now how do you deal with the garbage collection? That it's kind of the more your system's running, the more garbage collection needs to be done. And that can have an impact on your performance. So yeah, don't let cutting edge technology jump over a legacy technology. I like that picture. So my conclusions: letting cutting edge tech mature is actually a really good idea. Don't jump on new tech too fast. Make sure it's at least a little mature before you pin your projects on it when you're dealing with a project like ERAM, where it's very big and long. And picking the right tool for the job is important. Tools metaphorically come in all shapes and sizes. Make sure you're using the right one for the job. And WebLogic and JBoss Fuse both have their place. The Java system thrives in the web world, but C++ and Ada still very much have their place. And whatever you do, plan ahead for feature change or end of life. And the biggest plus we found with Java in general is the ecosystem for tools with continuous integration and testing. We're able to build and test ESAS every time a change was made and had 100% code branch coverage from our JUnit tests. And for ERAM, the story's not over. ESAS is running 24 hours a day with very low problem tracking and resolution rate. The team will be using this accumulated knowledge while engineering the next generation of the ESAS function within the ERAM program. So, any questions?
Thank you very much. That was fascinating. I think you hit on this issue towards the end, but one of the questions, at least I had, and I welcome others to write some in, is that distributed computing seems inevitably to also mean distributed organization, heterogeneous programming languages, processes, organizations, and so on. And clearly in a system as critical as the ERAM, verification and validation is a big deal. You have to not only make it safe, but you got to prove it safe and so on. You internally, sounds like you're using continuous integration. Are there external V&V organizations, and how have they, if so, and how have they dealt with this kind of heterogeneity and the ESAS and so on? Has that made their life harder, or have they managed to accommodate it as well?
It's made software's life harder more than the test organization, because the test organization just treats it like a box that they have to test. But then they take and run the software in various different ways because they're testing it, and Java does act differently because Java is a JVM. It doesn't start up the same way as a C++ application necessarily does. All the fuse logic stuff can take longer to load. And so if you don't build that in, they have run into problems and they kind of say, well, why isn't this working? So you have to build in specific things into the software to address for what other users might find.
You have some self-test capabilities?
It's basically an extremely self-test. There's more code written to test ESAS than there is to actually operate ESAS.
And that test code is running in the background all the time, or is it just running when you on your development environment?
There's two ways it's tested. There's a testing when it's built, so compile test, so the JUnit tests that I talked about. But internally, ESAS runs, we call it pinger, where ESAS itself takes messages from one system and sends them to another system. It simulates that event, and if it detects a problem in that, then it raises that basically.
Another question I had, you also mentioned a bit, was the Java garbage collector. For a system that's near real time, how have you managed to tame that? Or have you? I've seen a lot of pictures of wildlife.
It's basically untamable. It's wildlife. It's important. You have to be aware of it. The nice thing is operationally we run ESAS and nothing else on its server besides a couple of port things. So it's very much underutilized the max CPU. So we're not running into problems there. I wouldn't run it on a box that was running 80% CPU.
Yeah. So you've managed the resources to give you plenty of headroom, and interesting.
Doug,
please.
If I can ask a follow-up on this last one. So was there any validation method used to try to assess that you never go over a certain threshold of utilization? Or just testing?
It's basically, we've tested it, but operationally, the traffic flow unit doesn't send that many messages. So we have upper limits for what it needs to be able to handle. And so that is tested to make sure we can handle it. But it's so efficient that you can hammer messages through this pretty rapidly, and it's not going to create any problems. But that would be an important concern if you were using a slightly more complicated Java system, where it was doing more processing.
Okay, any other, sorry.
The system will evolve into getting more and more, because one of the things is that you have the system underutilized, so it's a nice place where to add new features that you occupy more CPU. So that's not a chance that it will happen, right?
That was in the original plan, and due to some issues I don't want to get into, never happened. So there was a thought of doing it, but it's currently just this little simple system without any additional capability.
Yeah, this is Alok. Can I ask a question, or can I tell?
Sure, go ahead.
Okay. So I work very closely with the brand. I'm the FA side. We work together. So it's more than 2 million lines of code right now for the ERAM, and more than 50% operational code is actually ADA. They uses 27 languages, then the other 26 occupies the other half of that, less than half of that, 65% operational code. So it's pretty large system. And regarding the CPU utilization and all that, the FA have a very stringent requirement, so even the baseline, no CPU goes more than 50%, so there's a lot of buffer over there, to accommodate any spikes and those, so that was not an issue. And most likely it will be changed now, because the experience is not very great with the Fuse, may go with some other products too. But all the future enhancements will be continue in majority of in ADA and then in C++. So ADA will remain the major language for the US in-route air traffic control, which controls 60% of almost world's transportation, air transportation. That's the backbone of the US, the nation's air traffic control. So we are very much alive into that.
Yeah,
that was my question for CPU. I mean, that's not a concern because there's such a high buffer over there, so you can accommodate spikes very well, once in a while.
One follow-up question, which I think maybe Alok, you just answered, was, this is a heterogeneous from a programming language and sort of development environment system now. Have you sort of feel like it's stabilized? I mean, maybe you might be changing some of the components, but the overall split between Ada, C++, and Java, has that stabilized? And do you feel now like it's the right answer? Or do you wish, gosh, I wish I could rewrite it all in just Java or rewrite it all in something else?
No, they're very happy with the Ada because it's
well, let me ask, let Brian talk there.
Okay.
Yeah, I think we're very happy with it. I don't think we want to use Java for a lot of the rest of VRAM. ESAS is its own little kind of not a big processing thing sitting off on the side. Whereas most of VRAM, what we have that's C++ and what we have that's Ada makes perfect sense. And that's where all the feature growth is happening. The ESAS is basically serving its own purpose and doesn't really need to expand right now.
Can you remind us what exactly ESAS is, what's role it's serving?
It's providing traffic flow messages, which are airborne reroute and pre-departure reroutes from the traffic flow unit. So if you want to change, it's rather complicated in the air traffic control system, but it's specific reroute messages that go into the flight data processor.
So have you been affected by COVID? I mean, have they said, oh, we have a whole new set of problems to solve, or is it like, nope, same problem?
More like underutilization of the system.
Yeah, I can imagine.
There's fewer planes out there.
Give you a little breathing room, and then they're going to all come back for certain. Interesting.
COVID affects performance, basically.
You mentioned the underlying infrastructure. Is there a separate internet just for this purpose, or do you use the commercial internet?
As far as I'm aware, FTI is its own separate system.
I see. It's internet protocol, but it's essentially a separate backbone or whatever. That's probably a good thing, given how many people have started. I mean, that would be one influence of COVID, is the use of the internet has gone up by probably a factor of 2 or something over the last 9 months, the commercial internet. Other questions from anyone? Don't be shy, just unmute and ask if you have it at this point. Okay, well, if not, let's thank our speaker. That's very interesting, Brian. And that's the real world. I think a lot of us are living in the world of sockets and frameworks and so on. And somebody's actually trying to apply all of these things. And you, as you say, you were on the cutting edge, the bleeding edge of this technology for at least in its early days. It sounds like things have stabilized and you're pretty happy with the results. But the getting there was probably not an easy process. And it sounds like you weathered that storm, but learned a lot of lessons along the way. Thanks a lot for presenting. And we now have a 10-minute break, and then we'll be back at 10 after 12. Thank you all very much.
Okay, thank you, Brian.
Okay, Rob, I don't know if you want to take over and introduce our speakers. That'd be great.
Sure. So welcome to the 11:10 session. We have two talks in this session. So the first talk is by Kyle Chard from the University of Chicago, and he will be telling us about productive parallel programming with Parcel.
PPP.
Right, very alliterative.
Take it away, Kyle. Kyle, are you there? There he is. We can't hear you, even though you're not officially muted. It looks like you have a local muting going on, or you're.
I do. I was
There
just
we go.
saying I've got so many buttons to unmute myself that I think I'd be good at this by now. But that's, I don't know. It feels like every time there's more. Let me try and see if I can share that. This is my first presentation on this setup, so I'm trying to work out how to. Alright, that's not going to work. Let me unplug from my. Go back to the traditional way without external monitors connected. Oh, screen sharing stopped. You'd think we'd be good at this by now, wouldn't you? Okay, let's do that. Okay, that's now working.
Perfect.
Well, thank you. Okay, so good morning, everyone. Yes, so thanks for the introduction, Ms. Rob. Yeah, so I'm Kyle Chard. I'm a research assistant professor at the University of Chicago, and I also work at Argonne National Lab. And I'm going to present some work here that we've been doing over the last 3-ish years with colleagues at UChicago, Argonne, Illinois, and more broadly. So I thought to start with, given that we're probably operating at a slightly higher level than many of the talks that we've seen over the last couple of days, I thought it might help to level set to explain a little bit about the types of workloads we're running. So one example workload here is, so I should, I guess, implicitly state that a lot of our work is really focused on addressing scientific problems, particularly on large-scale, high-performance distributed computing systems. So one example is work we're doing with the Dark Energy Science Collaboration that is a 700 or 800 person collaboration that is planning to investigate dark energy based on data coming off the LSST, now called the Rubin Observatory. And so they have several workflows. One of them that I thought would be most interesting is a sort of bag of tasks style workflow where they're trying to simulate, the LSST is not online yet, so they're trying to simulate what the images might look like so they can start building the rest of their analysis pipelines. And this sort of model basically, it's a fairly simple model. They have tens of thousands of these instance catalogs, which basically describe things in the sky. They use these instance catalogs to then simulate each of the 189 sensors that is going to be on the LSST. And these are, of course, all, as you all well know, in parallel and distributed world, they're all very different sized tasks. So the real problem becomes, how do we take all of these tasks, 189 times tens of thousands, how do we bundle them up into units that we can cram onto nodes? And then how do we distribute that across a large system with thousands and thousands of nodes? In this case, we're using Singularity, which is a container technology. We cram them all together and then we allocate them. They run for anywhere from probably tens of minutes through to tens of hours. And at the end of it, we end up with these very nice pictures of the sky at very high resolution. So this is really a fairly simple bag of tasks style workload that we just need to parallelize and distribute across nodes. Another example is recent work that some people at Argonne and some of the other DOE labs have been doing is to basically screen billions and billions of molecules to try and work out which ones might be effective as therapeutics against COVID-19 before they go off for trials and labs and people. And so this is more of your workflow style, data flow style analysis, where essentially we can parallelize this at a very low level. We take in these very small molecules, we canonicalize them down to a common form, we compute a bunch of features, these are numerical features, we compute fingerprints, we compute images of them, and then we pass these basically into machine learning models that again are running in very short period amounts of time to basically compute projected docking scores of whether or not these proteins, whether or not these small molecules will dock to these proteins. And then we fire them off for much more, the leading candidates, we fire them off for much more detailed computational simulation. So this is a more data flowy style application where you're seeing small amounts of data progress through these stages, and we're making decisions as we go about which ones we need to carry on to more intensive computational simulation. And again, I guess the common thing about our workloads is a lot of them are running on these very large scale computing resources like Theta at Argonne or Frontera at TAC. And TAC, just, well, I guess, Rob, you're running this, sorry. Just keep me posted on the time because I don't have in this presenter view, I don't have the time. So yell at me when I'm getting close to the end.
15 more minutes and then we go to questions.
Awesome, okay. Yeah, so I can adapt the talk depending on how we're looking. So in terms of motivation for our work, I think this is pretty common across most of the talks we've seen today, with a couple of sort of subtle differences. So the first is obviously that this parallel and distributed computing thing, once perhaps a little bit niche, is now becoming sort of common to everyone. And most of the scientists we work with, anywhere from your traditional high energy physicists through to archaeologists, they're actually requiring the ability now to scale their codes across at least a single node with many cores, and often cases across many nodes. The second thing from our perspective is that a lot of software we work with is assembled rather than written. And what we mean by that is that people are coupling together bits of code written in different languages to basically try and orchestrate their scientific analysis. And so you can think of this in a simple term, something like TensorFlow, that provides these nice APIs to wrap more complicated low-level programming. But also, especially in science, like we saw before in the cosmology workflows, we're actually wrapping quite large chunks of code that need to be parallelized, often at the data parallelism level. And the third thing in our world, and I think more generally that we see, is that Python has very quickly established itself as one of the most productive and popular environments for programming in general. And we're seeing this thriving ecosystem of libraries, tools, Jupyter notebooks, infrastructure to support Python-based workloads. And so it's these three things that really motivated us to develop the Parcel library. So I have a one-side sort of description of what Parcel is before we get into a few of the details. So Parcel, as I said, it's just a Python library. So rather than in previous efforts, we've actually built domain-specific languages to accomplish these same sort of goals. And as I'll talk about a little bit later, 3 or 4 years ago, we realized that for our user community, it doesn't make sense to give them sort of a very powerful but very specific domain-specific language. And it's better for us to perhaps to try and stay closer to an existing language that the scientists are used to working in, even if we're losing a little bit of performance. So in the Parcel model, you can think of this very, very much like other systems you've probably seen before. Essentially, we define what we call apps. We annotate them with Python decorators. An app can either be a chunk of Python code, just a Python function, or it can be a call out to an external application, basically invoked via Bash, but it could be Java, could be Fortran, could be a series of crazy scripts. We use futures basically as a proxy for these results. So asynchronous execution, we call one of these apps, we send back a future. The Parcel runtime system handles when that app will execute, when and where that app will execute actually, and sends back the results or points to a file that's been produced by that thing that's run. We implement a data flow model. So essentially we compose a dynamic dependency graph in the Parcel system. And then we link together, sorry, it's early here, so my throat. So we link together these apps and determine the dependencies of those apps. And when they're all met, we basically send them off for execution where they can run. The other thing we've really focused on with Parcel is trying to make the programs portable. A lot of our, as you saw before in the cosmology app, these researchers, they like to scavenge and take as much computing resources as they can. So they very much like to move from one machine to the other, depending on where they can get an allocation or where they can get computing time. So I thought I'd talk a little bit more about how the actual programming model. Normally, I'm more of a systems person, so I normally speak to systems conferences. You have to excuse my my bias towards showing you graphs about scaling and things, but I'm going to try and talk a little bit more about the language side of things. So we have this this data flow model, which we think provides a fairly intuitive parallel programming model that people can understand, at least our user community. And so essentially this data flow model obviously comes from the lower level, but I think a lot of people now are adapting it to the higher level programming models. And essentially we just assemble this dynamic directed graph of data that flows between tasks. And in the parcel model, this data flow system, we allow data to be exchanged in terms of raw Python types and objects that can just be passed between these apps, both as input and output, the same way as you normally would, or as files, because a lot of our science communities are very, they have their systems and their codes are already set up to basically produce and ingest files. Because we're used to running in distributed environments, these files, we describe them as including the transfer protocol, the mechanisms we need to actually move these files. So we allow people to basically use FTP, HTTP, or Globus to move these files, and that allows us to create these data flow graphs that can span different nodes and even different computing systems in some cases, although much more frequently different nodes. So what does this look like in practice? So this is an example of a parallel geospatial analysis where you take in some images, you annotate them, you color them, you analyze them, and then you produce some different outputs. So this is an example that we call the MODIS workflow. And so the basic approach from a parcel perspective to an app like this is generally these components here, all these nice colored components. Researchers have these sitting in some library, or they have many of them, and they need to produce the glue code to actually connect them together, to parallelize them, to run on very large sets of data that they'd like to analyze. So when you have a problem like this, you have this graph, everyone's got this graph in their mind, and how do you translate that to something that you'd like to actually run in Parcel? So the first thing you need to do is you need to define these Parcel apps, and that's a case of wrapping Python functions. As I said before, we have this bash app decorator where we can say, here's this land use simulation script, which probably calls a bunch of Fortran code or something else crazy behind the scenes. And essentially this app wrapper is just a function wrapping the actual invocation on the command line. So you can see there, we're just calling out to land use sim, and we're passing in the input image. And we're also describing what the output files that will be produced from that call are, because that's important to us to be able to track, as I said before, that data flow operation, so we can pass the output chunks into another app. We might also have a Python app here. So fortunately, this color package, and this is obviously, I didn't want to give you walls of code. So this is very abstracted to something that's not quite real, but hopefully paints the picture of what this model looks like. So the Colorize app might again take that same image and might produce some outputs. In this case, the outputs might be produced by a Python piece of Python code. And so again, here we're just calling that package that might be some library that we've borrowed from our friends at another institution or what have you. And again, we're just passing here a call to the color package with the image. And here we're only saying how many outputs, how many chunks we want to make, because these things have very formulaic, these apps have very formulaic file patterns where they create files of the same name and number them, etc., or they throw them in HDF or some other format. And then we might have some sort of analysis app that takes all of the chunks from the land use app and all of the chunks from the Colorize apps app and combines them together in some way. So this very MapReduce style operation where we're fanning out a bunch of tasks to land, reduce, and colorize, and then we're bringing them back together into that analyze app to combine them. And then how do we actually combine these things from the Parcel perspective? So typically people create these libraries of apps, and then they write fairly standard Python code to actually connect them together. So here we're just looping over a bunch of chunks, and we're calling that land use app to go and create these outputs. You see here, here's a formula for how we're creating the files that are created at the end. The Colorize app, of course, as we said before, we don't need to loop over it. We're just calling it, and it's going to produce a bunch of chunks. And you see here that we're specifying in both cases what the outputs look like, which are just flat file names. I probably should have included an example here with Python objects, but I didn't. And then we call that analyze app by passing in essentially the outputs of each of the previous apps. And so Parcel behind the scenes will call these two functions. It'll keep futures for each of these files that's going to be created. It'll wait until they're actually created before calling that analyze app with those inputs. So in this example, I thought it would be worth just digging into how does this actually work in practice when we're running on a couple of different systems. I should also say that we implement a dynamic task dependency graph. So a lot of our other workflow systems that we work with, they use more of a static dependency graph. So essentially they almost compile down an application into a static dependency graph of all the things that need to run. In Parcel, we focus more on a dynamic model because a lot of our workloads tend to change as they're going. So the dynamic model means we're just keeping in memory this graph of dependencies, and as tasks are running, we're adding or removing from that graph, changing the graph that's going to need to be run. So an example here where we're running, this is a simple example of a Monte Carlo pi simulation. Essentially, as we start running the app, we start to establish this graph. We have connected resources here that are on Amazon or the exceeds the NSF cyber infrastructure provider, just a combination of supercomputers. So we have this DAG that is starting to be assembled in Parcel's memory. As soon as any of these tasks in the DAG are ready to run, we ship them off to whatever resources are connected. So we're shipping them off here to Amazon to run on the Amazon cloud. These tasks come back again, and as a result of these tasks coming back, we can complete the next part of the graph. So we have these green, purple, and orange boxes now ready to run, which again is, if Parcel has available resources, it will ship them off for execution in these different computers. So how do we enable portability in Parcel? So as I said before, it's important for us that these programs can be run on different machines. Our users run them locally, often when they're just developing their app. They run them on grids, clouds, supercomputers. And so we have this abstraction called the provider abstraction that allows us to speak to different types of system schedulers, cloud APIs, etc. We also, sorry, I thought Tucker was going to say something. We also have an abstraction for how we actually execute these different workloads. And we did this because a lot of our users are using very different types of programs. We see a lot of high throughput things, something like that cosmology example, where people are basically running thousands and thousands of tasks on hundreds or perhaps thousands of nodes, perhaps for days, and they really care about the usability, reliability, monitoring, etc. We have some other people that want to run on the entire every node in a supercomputer, and they want to do that at very fine-grained parallelism, so you're running on 200,000 cores all at the same time. For those types of workloads, it's hard for us to keep up with the throughput required. So we have this extreme scale model that allows us to run basically as a distributed MPI job. And then we also increasingly have interactive and real-time workloads where people are running on a few nodes, but they want it to happen quickly with low latency. So we built we basically took Python's concurrent futures executor interface, and we implemented things that went beyond the single node. So we implemented a high throughput executor, we implemented an MPI-based extreme scale executor, we implemented a low latency executor, which basically just is the high throughput one with everything removed that takes time. And the good thing we've found with adopting this common interface is that it's allowed other people to contribute executors for particular examples. So we have an IPy parallel executor, we have a WorkQ executor, which is a system developed at Notre Dame. So if I understand correctly, I've got about 3 minutes left, is that right? Okay.
Right.
Right.
Okay, so as every good presentation, we've done some scaling tests. So we ran this on the Blue Waters system. The takeaway here is really that these executors can scale to hundreds of thousands of concurrent workers running on probably on the order of 4,000 to 8,000 nodes. But the one weakness there is the throughput. So we're getting on the order of 1,000 to 2,000 tasks per second. So if you're running very short tasks, that's not going to work very well. So let me just quickly mention, so I've got 2 minutes, so I'll mention just a couple of things about where we've come from. So our group's been working in this sort of area for about 20 years. We developed the Swift system before Apple built their own Swift system, which caused us a few problems, or programming language. So Swift was a programming language that really focused on creating these types of parallel workflows. It was a domain-specific language. It looked a little bit like C and Java, but it really was its own language in a lot of ways. And this allowed us to write some great papers. It allowed us to show some amazing performance. It allowed us to work very closely with scientists to actually implement very efficient scientific codes. What it didn't allow us to do was to actually grow a broad community of people using this type of technology. And so around 2017, we sort of looked back and said, we've got some amazing success stories, but we haven't really democratized this to a bunch of people. And the biggest weakness was most of our user community really is just uninterested in learning a new language to achieve their science. So in 2017, as I said before, we focused on, well, how can we take as much of that as possible and bring it to Python, bring it to the actual environment that they're working in. And that's what led us to develop Parcel. And I think so far in the last 2 or 3 years, our adoption has been much broader than previously in Swift. And I think it's still meeting the performance goals of the science community we're working with. So with that, I'll conclude. So just a quick summary. We think Parcel provides productive, safe, scalable, and flexible parallelism in Python. By productive, we've tried to just minimize as much as possible to make it Python with as few little extras so that people can sort of fairly quickly understand the Parcel environment. Safe, we think of this deterministic parallel program through this, this DAG model as being a safe way of representing parallelism, where we allow people to construct that. We as the Parcel runtime can interpret it and make sure that we're avoiding loops and things like that. We think Parcel's relatively scalable and portable with this abstraction model of executor and provider. We can move programs around fairly easily. And we think it's a flexible model and that we can allow this composition from a bunch of different components to create an application. So with that, I will go to questions. Thank you, everyone. It's a real shame we weren't all able to be there in Chicago. I would have very much liked to meet everyone and be able to discuss some of this stuff, but we'll make do with Zoom.
Okay, thanks, Kyle. So we have several questions in the chat. So I guess I'll just go through them. So the first question here is from Tuck, and it says, does Parcel support replication or sharing of distributed data structures, or is data always passed as essentially a parameter in a kind of remote procedure call?
Yeah, so at present, it's all passed as a remote procedure call. Some of the systems that are similar to Parcel in some lights, like Dask, I don't know if people have heard of Dask, which is another Python library, or Dask, depending on your accent. That has abstractions, data abstractions that you can, like you define your own NumPy array, and then the Dask runtime splits that up and runs it over different things. But in Parcel, we have that very strict contract of data in, data out.
Okay, and then I had a related question. So in the example you showed with the analyze node, and then I forget what the nodes were, but there were like two parallel nodes kind of feeding into another node. I think it was like your first example. So I was wondering if there's any parallelism going on within the nodes, or if it's just across nodes. I mean, not node graph. I mean, like.
Yeah, so you're asking, are we only in? I'm going to get this wrong. Are we only inter-node, not intra-node, right? You're asking, do we only parallelize across nodes?
Right.
Yeah, so we parallelize down to the level of cores. So essentially, I didn't, okay. Is that the question?
Well, yes. No, sorry, maybe node is a confusing term. Because that also has meaning in the context of a computer architecture. I just meant in this graph, like, does each oval in the graph represent a unit of sequential work, or is there parallelism going on within an oval?
No, yeah, so great, yeah. I was 100% confused with the word node. Yes, node and graph, not node on computer. I understand. Right. No, so each of these ovals is the smallest granularity of work that we have, and we basically parallelize at that level. So I didn't explain this at all well, but these little rectangle chunks are essentially the chunks coming out of that. So we pass in, say, one image to this land use app. We iterate over it, I don't know, 1 million times to get 1 million different chunks out of that app that then are passed on to the next thing.
So then, does that create an issue for load balancing?
Yes.
Okay.
Yes, most certainly. So load balancing is probably our single biggest issue, right? I mean, we're taking all of these. So on this graph, we've got all these green boxes, all of these blue boxes, the purple ones, the red ones. They all run for different lengths of time. If we ask a user to tell us how long they're going to run for, they get it wrong by at least 2 orders of magnitude. So it's a case of how do we actually take these boxes and put them on a system? How do we allocate them down at the core level or the node level, depending on what we're doing? There are always stragglers, so there's always this make span problem where we're the tetracy problem that I'm sure you're all aware of how do we schedule them in order such that we can minimize the overall time and maximize the utilization of the system we're working on.
Okay, so then I think that relates to another question that I had here, which is that how does this relate in general to HPC, high performance computing? So, and I guess I could take a guess at that. It sounds like there's some overlap, right, in the goals and what they're doing, but it sounds like there's kind of different communities of people that maybe the HPC people would be more focused on performance, HPC meaning high performance computing, right? And maybe that this community would be less focused on performance and more focused on kind of programmability. Is that fair?
Yeah, that's exactly right. I mean, we're trying to sort of walk that line as well as we can to make something that's easy to use for a fairly broad range of people, but also gets as much performance as possible. But surely, I mean, you're going to get better performance if you take all of this and implement it in MPI, right? I mean, if you can implement this thing in MPI, it's going to perform better. If you can actually use very low-level parallelism, it's going to perform better. But most of the communities we work with just don't have either the time or expertise to actually be able to do that. And these codes are already often written in different languages and things. So in a lot of our workflows, actually, pieces of the code are written in MPI. So some of these oval boxes might be very highly optimized MPI code that's going to run over 5 nodes. And what the researchers want to do is they want to run 1 million of those 5-node MPI things. Plus, they want to tack on some Python machine learning at the end of it. Plus, they want to tack on maybe something that runs well on half a node using whatever parallel, like lower level program parallelism you want to use for that node level.
Okay, I think we have time for one more question. So someone asked, are you not limited by Python GIL, or is Python just only used to manage and control processes?
Yeah, that's a great question. So probably every slide I should talk about the Python global lock interpreter. Yeah, so essentially that's only at the control level, right? So what we're doing is essentially we're cutting up all these tasks for execution, and we're just sending them off to a queue for running and for running on different resources, and basically a queue coming back again. So the interpreter lock really is only hurting us from the control perspective. Most of the work's happening in these asynchronous processes that are running elsewhere. So you can
they're
think of
typically
it like
not written in Python, right? The actual app.
Well, some of them are written in Python, but of course they're running as little fragments of code in their own Python interpreter off their own. Like every core, if we're running core level parallelism, we have a Python interpreter spun up on every single core we're running on. So we've actually shipped that over a ZeroMQ pipe. We use ZeroMQ everywhere. Ship it over ZeroMQ down to the worker. The worker's got its own interpreter, has all the dependencies, runs that piece of code, ships it back. So I know, Rob, you probably want to get to the next person, so I'll end my answer there.
Okay. All right. Thank you very much.
No problem. Thanks, everyone.
Thanks, Kyle.
Okay, so the next talk will be by James Munns from Ferris Systems, and he will tell us about building a culture of safe and performance systems with the Rust programming language.
Great. Now I'm unmuted. Can everyone hear me okay?
Yes, I hear you.
Excellent. Great. Then I'll go ahead and get started. Let me start my timer so I don't run over. Yeah, so this is a presentation about Rust for this. I couldn't come up with a more succinct name, so I had a very descriptive but very long name of building a culture of safe and performant systems with the Rust programming language. So I'm James. I'm a managing director at Ferris Systems. And I tend to talk about Rust a lot. My background is actually in embedded systems, so my distributed systems tend to be much, much smaller, but there tend to be a lot more of them in most cases. I work at a company called Ferris Systems, who does consultancy and training and a lot of different things in the Rust programming language, but we work across a wide variety of domains, from high-performance backend systems to robots to connected wireless devices to all kind of compiler tools and other things like that. So this talk is about Rust, and like I said, I talk a lot about Rust, and we've got about 80 slides today, so I'm going to be moving pretty fast. But I think Rust is an interesting language. Obviously, I'm working at a consultancy that focuses on the Rust programming language, and I've spent a lot of the last couple of years contributing to the open source project. More reasons than I can cover in one talk, but I want to cover a couple things that I think are particularly interesting about Rust, particularly in domains such as distributed or highly parallel or highly performant computing. I think that Rust is a relatively new language, so it's only been stable since about 2015. But in those past 5 years or so, Rust has been showing itself to be a language that is going a lot of places, whether that's big high-performance back-end computing places or very tiny embedded systems places or sort of in-between places like web front ends and things like that. But it's important to remember that Rust as an open source project, or as any project, is a language that is made by people. So the people that contribute to the language, the people that use the language, and the people who are part of this whole community. And this seems like sort of an obvious thing, but as we'll see later, it's a pretty important thing to consider. Personally, I think that it's pretty impossible to separate technology and human concerns, especially when you hit a certain scale of project. Whether you've got 10 researchers working on one project or thousands of contributors working on one open source project, we are a system of people who are building systems. And this kind of has some interesting back and forth effects. from both a technological and a human perspective. So it's sort of important to understand where Rust came from. Where did it come from? What inspired its design, and what has caused it to be in the place that it is right now? So if we look back to the beginning, kind of the beginning effects of Rust, we're looking back at 2010 or so, which feels like a long time ago, especially this year, which has felt especially long. But we're looking back at Mozilla in 2010. So in 2010, Firefox was pretty much written entirely in C and majority C++. Now, the thing about 2010 is it was before the 2011 version of C++ and before the 14 and 17 versions of C++. So this is before some of the more modern conveniences that were available to help you write more correct or more performant code in C++. And this led to a lot of problems, particularly the scale of a project like a web browser. Especially as computers became more and more parallel, there were more and more difficulties on getting things like thread safety or memory safety correct in practice. Despite all of the code reviews and best engineering practice and static analyzers and all of the things that people tried to layer on top of languages like C and C++, year over year, they still had issues with either exploits or crashes due to memory safety and other related bugs. Now, this is one of those things that actually hasn't changed significantly in the last 10 or 15 years. Year over year, memory and safety bugs tend to cause approximately 70% of reported CVEs or publicly known vulnerabilities. And this is a study that's been seen over and over by larger projects like Microsoft's entire product line, the Chrome OS browser, Flash or Adobe Flash, and Mac OS. So they've actually done studies of all of their CVEs and found that plus or minus 5%, the majority of these CVEs or safety problems are due to memory unsafety problems. So around this time, Mozilla was considering what their options were. And one of the engineers at Mozilla said, hey, I have this hobby language, and I think I have a way of addressing memory safety from a more fundamental level. So rather than something that's layered on top of an existing language like C or C++, why don't we write a new language with slightly different paradigms that allow us to categorically rule out things like memory safety? So this is from the presentation at the Rust All Hands at Mozilla in 2011, where Mozilla was actually introducing the Rust project internally. They described it as a new systems programming language designed for safety, concurrency, and speed. And at the time, it was originally a hobby project, but now is being built by a team within Mozilla Research and within the open source community. So Mozilla is a company with a very strong open source background. And so they took the Rust programming language under those same paradigms as they did their open source browser efforts. They asked, what if it was easy to leverage concurrency? What if it was just as easy to write something that was multi-threaded or concurrent as it was to write something that was single-threaded? And what if it was possible to do this without overhead, like other languages that use things like an interpreter or garbage collection to achieve these goals? What if we could have all the performance of C or C++ with all of the convenience and correctness of slower interpreted languages? So over that period from when it really entered main development efforts from 2011 to 2015, the Rust programming language changed a lot. It invented a lot of stuff and it threw a lot of things away. And it took a lot of inspiration from many different places. There were research topics that were introduced. There were other languages like Erlang and Haskell that put their flavor on Rust. And generally the research interest of Mozilla and their actual practical use case of developing a parallel first browser engine. So what did Rust end up delivering in its 1.0 release in 2015? Well, it managed to deliver a surprising number of technical advancements, either taking things that were fairly new from research and shipping them in a production grade language, or combining concepts from many different languages and areas of research into one consistently usable systems programming language that's suitable for these kind of low-level implementation techniques. The first of these is the concept of ownership, which is in some other languages referred to as move semantics. So by default, Rust is a language that makes ownership or move semantics by default. So it's a language that says when you pass something by value to a function, you no longer have access to that. And this isn't a concept that originated with Rust, but one of the first languages in this domain to really reach widespread acclaim for these kind of techniques. So what I mean by this is if we have a function that says that it takes a string, and we have, let's say, two functions here that take a string. If we try to create a string, pass it to the first function, and then pass it to the second function, we're actually going to get a compiler error because our compiler is going to say you moved this type to this function, and then you tried to move it again here, which says you're using this after the move, which means this isn't going to compile. So we can see that we have compiler enforced move semantics that don't allow you to accidentally use data in a way that you don't expect. Now, the flip side of this is borrowing. So people often use languages like C and C++ because they have access to passing by reference or using pointers or references to share data between different contexts. Now, Rust has a slightly different kind of enforcement here, where Rust has said when you borrow or when you are borrowing something, then the caller no longer has access to that information. So if we have a slightly modified version of that first example, where this first function takes a mutable reference, and in Rust, all of these references are immutable by default. So you do have to explicitly say that this is a mutable reference. This function is able to mutate that string during the context of this function, which means it's allowed to make modifications, but not creating or moving a new value, while still having other functions that still take it by ownership. So now our example is changed to passing a mutable reference to that first item and passing by ownership to the second function. And something that goes really strongly with this concept of borrowing is a concept of lifetimes. And lifetimes are a way about reasoning about how long does this borrow of data last. And this is really important to make sure that we only have data that is borrowed for a specific amount of time so that the compiler can reason about whether multiple borrows or borrows and storage in different places are sound to do. So, for example, we can annotate a function that takes a reference with lifetimes. And in Rust, these little tick notations are naming these lifetimes. And while you don't always need to annotate these, particularly for simple examples like the first one that I mentioned, when you have a function that takes two different references and returns one of these references, it's actually really important for the compiler to be able to reason about which reference am I getting back? Am I getting back a reference to my haystack, or am I getting back a reference to my needle? And this allows the compiler to reason about these borrows at compile time to make sure that you're using them in an appropriate way and make sure that you don't accidentally hold on to something for longer than it is valid for, which is a really common use of use after free vulnerabilities. These can also be annotated within structures, and this is one of the most common times where you'll need to annotate these, because you can store those references within a structure or a variable. So when this other variable is holding on to this reference, it's really important for the compiler to be able to reason about, hey, how long is this data that I'm holding on to really expected to live? And this is something that the Rust compiler can do entirely at compile time, because it has these language functionalities to really reason about how long does this data live for, and is it valid to be doing the kind of things that I want to be doing? Now, to enforce all of these concepts, the Rust compiler has this aspect called the borrow checker. And as I mentioned, this is a static enforcement of language concepts. And in most cases, it's really just strictly enforcing the best practices that you were supposed to be doing in C and C++. Who's in charge of allocating memory? Who's in charge of freeing memory? When can I have multiple contexts that have access to the same data? Now, when most people first start working with the borrow checker, their first experience looks a little bit like this. They get the compiler saying, no, you've done it wrong, and this is unacceptable. Because Rust is a fairly strict language. If you don't get things correct, it won't let you compile your program. And while this feels sort of aggressively strict to a lot of people when they get started, most people, when they start using Rust, actually really like this, because they can rely on not making these mistakes at runtime, which means they don't find this after their program's been running for an hour and is 90% of the way through a data simulation. Their program just never runs if they got the code incorrect. To kind of really boil down to a short presentation about what the borrow checker enforces is that any reference can either be shared exclusively or mutable. So you can have a mutable borrow of data, but then only one piece of code is allowed to have access to this. This prevents you from having multiple aliased mutable accesses, which are the root of a lot of correctness problems in programming. But if you only have read-only access, you can share that with as many different contexts as you like, because no one's allowed to mutate it, which means it's going to be consistent for the total lifetime of that borrow. So this is one of those things that boils down to a really simple rule, but has really huge knock-on effects in wide-scale programming. Now, Rust also has a stronger and more expressive type system than you might be used to from languages like C or C++, but might be, on par with what you're used to if you program in languages like Scala or Haskell.
Beta.
There's
5 minutes.
5 minutes left, right?
Sorry.
I think mine started about 5 minutes late, correct?
It started about 1 minute late.
Okay, then I will move very quickly. All right, so I'll skip through the type system features because there's a lot of them. But I want to get into the other main aspect that Rust, I think, has done correctly. I do want to hit on send and sync, which are two particular traits in Rust, which allow you to share data safely, either sending from one thread to another or sharing data between different threads. But I'm going to move on to the other thing that I think Rust got correct. And I think that is a concept of sociological advancement. So Rust, as I said, was a distributed programming language, which allows it to have a lot of cooperation between different people. And when you're working with multiple people, you have to consider your weirdness budget or idiosyncrasy credits, which means when you have things that people don't understand, they tend not to like to use those. Now, in the early days, Rust was an ever-changing and ever-weird language, and it kept this in mind and thought about how it paid down that budget. And Rust made a couple key decisions along the way. So in Rust, as I mentioned, safety is strict and non-negotiable, which means that dangerous code should be very obvious and ideally not necessary. And it turns out people really like that because it lets them consistently reason about the language. And things like documentation are non-optional and non-trivial features because people won't use what they don't understand. And it's important that you give names to concepts that people are expected to know so that they can effectively use the tools that you give them. So for example, this isn't just in documentation, this is also in the output of the compiler. So this is what a compiler error looks like in Rust. And this seems like a lot of information, but this is providing people with a context of why their code is wrong and what to do to correct it. So they're not just left feeling, oops, I'm wrong and I must be done. They're told how to correct the kind of problems that they run into. So kind of one of these mindsets is that there are no bad programmers, there's just insufficiently advanced compilers. So your compiler should help people grow as much as your documentation does. And Rust does a number of different things like making consistency the default with things like code formatters or just an ethos around the language of being consistent, and using tools to build tools. So people are using the Rust language to build tools that makes the Rust programming language and building in the Rust programming language better. And when you make it easy for people to build, use, and share tools, they end up solving a lot of problems that you didn't even know you had or other people in the community didn't know they had. And it's important to think of that community as a non-optional and a non-trivial feature because the hardest problems are people problems in most things. And it's important to think about sharing and teaching while you're working on all of the hard technical projects as well. Because you need to bring new people into your project and constantly be bringing them up to speed with the expectations of what your project are and how your project works. Because all complex systems include a subsystem of people, and it's important not to forget that, because if you do forget that, the human factor can often become your limiting reactant to success in your projects, because if they can't use your project effectively, they're just going to leave. So it's important to change the mindset from a project perspective as much as it is from a technical perspective when you're trying to challenge new technical milestones, whether that means looking at things like, oh yeah, it's terrible and the documentation is bad and there's no good examples, but you get over it after like 6 or 12 months. But you could instead be saying, how can we provide an on-ramp to people to make what we're doing the easiest and most correct way to do things? Because then people will migrate to your project and really like using the project that you're doing. Or by helping people learn rather than saying, oh, it's a hard language, so it's going to be really challenging. You know, Rust is this hard systems programming language. So if you don't understand it, you must not be smart enough. But instead, Rust takes this technique of, if something is unclear, that's considered a bug in the tool or documentation or library or compiler and should be fixed just as much as any other technical bug would be fixed. Because if we lose our community, then we've got nothing left. So this approach has worked for Rust. And although the experiment is ongoing, we think this is something that has really been one of the reasons why Rust has been adopted so quickly in so many different areas. People just like working in the Rust community because they have a lot of shared values. And this combination of tech and humanity has brought people to Rust and really kept people there, even when they're moving into areas where Rust isn't super well supported already. And maybe this kind of approach could work for your project as well, too. So I'm James, and this has been a very quick presentation on building a culture of safe and performance systems with the Rust programming language, and I'm happy to answer questions now.
Okay, thanks very much, James. So we have several questions in the chat. So Richard mentions in the chat that he has some high-level questions that he'd like to ask over the mic. So Richard, why don't you go ahead and ask your questions?
Yeah, due to the huge number of questions there, I'm going to make it a comment and then a question. So the comment being, I just find it interesting that, just in case you didn't know, that the goals that you mentioned about Rust, namely concurrency, easy concurrency, safety, and particularly the human aspect, were actually core design goals of the Ada language. I don't know if you know about Ada, but I always find this interesting that the Rust community mentions that as if it's like this new thing, that, oh, we had this idea to do this, but it already existed in a very well-proven language. So I'm curious about that, but let's not make a question. The real question I have is on that, on safety. So with Rust, it has this tendency to halt and catch fire when things go wrong. So like panics, and you have to explicitly handle a panic or else the program actually ceases to execute immediately. And I wonder what the thought is on this from the safety perspective. If you're talking about embedded systems or actual safety critical systems, you really can't have the program just stop because something goes wrong. And one example in particular is that if you take a slice of a string, which is in UTF-8 encoding, and you're slicing a portion where the first character you know is greater than 127, you get a panic. And that's a little less obvious to handle than it would be, you know, getting a result enumeration, for example, back from a function. So kind of, what's your thoughts on that?
It's a lot of stuff. So Rust is definitely an open source project. And as you mentioned, very rarely is Rust the first language to invent anything. It's rather a combination of different things at a certain scale of either contributors or users and things like that. So certainly there's, as I mentioned, Rust is willing to steal the best ideas from anyone, whether that's C or C++ or Ada or Haskell. Rust is very shameless in its ability to steal and combine best ideas from wherever it can find it. So that's one aspect to that. I'd say with respects to panicking, so panicking is an explicitly safe operation because it's better to stop the program than it is to continue on incorrectly.
What if you're
when you
running
go above
avionics? Sorry, I'm still going on if you don't mind. So it's one of those things where this is actually a systems engineering concern rather than a programming concern. How you handle this is a whole systems program aspect, particularly embedded. So my background is in avionics, and honestly, when you hit a hard assert in avionics programs, you do typically restart the application. You know, you have these fail-safe abilities, and you will typically fail over so that if you have a redundant system, that second redundant system can pick up on that. So a panic actually can be a correct handling thing. Although in Rust, it is not considered. Sorry, let me.
Well,
in Rust, it's considered.
I just wanted to make a follow-on point to that. I think you can handle panics, right? So you can create a panic handler, so you don't necessarily have to halt and catch fire. You could do something else.
So yeah, panics are a very large, complex question. In embedded, you typically have panic abort, which means you will abort the program when you stop. But on a desktop, there is the possibility to catch and unwind panics, sort of like exceptions. But that's not mandatory. But I just wanted to say that Rust as a language, generally, it's considered bad form to panic. It's definitely strongly recommended to use things like the monadic option and error result types to handle problems. So Rust does have those capabilities, but it is certainly seen as bad form in most cases.
Okay, so So there's another question asking about comparison with Go. So Tuck says that Go is used extensively for distributed computing. So he's wondering if you have any points of comparison between Go and Rust.
Yeah, Go is an excellent language for the domains that it tackles. It solves these safety problems. Well, it mostly solves these safety problems by having a runtime or a garbage collector that allow it to make stronger domains. And Rust made the decision that that wasn't something that was acceptable for the low-level systems programming that they were looking to achieve. As I mentioned, there are languages like Java or Python who have generally solved in most cases things like memory safety, but they do it with a level of overhead that isn't always acceptable for avionics or browser or operating system development. So there's a lot of different approaches to do this. I think Rust's particular interest is doing this almost exclusively at compile time rather than needing to bring in a runtime or allocator or things like that to achieve those goals.
Okay, I guess it's time for the panel now. So thank you very much, James, for that talk. And I'll hand it over to Tuck now.
Thanks so much.
Well, don't go away, James, because you're on the panel. So people get a chance to ask you more questions, and that was sort of one of the schemes here. So thank you very much. And in fact, Richard is also on the panel, and Kyle. So we've managed to pull in a number of the speakers from today. So if there are some questions that you didn't get a chance to ask, this is your chance to do so. The overall theme of this conference has been trying to bring parallel and distributed computing to a wider audience. And one way to do that is to build it into the language. And certainly as with Ada 22X, we're trying to build in more parallel programming. And distributed computing, there are a few languages, if you will, that have it built in some sense. Parcel is a language/library combination that has it built in. But then on the other hand, there are things like ZeroMQ, where if you're doing distributed computing, you're definitely aware of it. You've got sockets and you've got different kinds of sockets and so on. And to some extent, OpenMP is also, you're really aware that you're doing parallel computing, but there are ways of doing it that reduce the complexity for the user. So, so in this panel and in the workshop, the overall workshop, parallelism is beginning to get fairly well understood. A number of languages are now building in parallelism, but I would say there are very few, if any, languages that are widely used that have distributed computing built in. They certainly have many, there are sockets and things like that that people can use, and ZeroMQ makes that very elegant. But the question is whether we could go further than that. I think Rust has some features that allow you, thanks to ownership and so on, that you can have, you sort of know who owns the object, and that makes it easier to safely pass it to somebody else. You can, you know, where all the pointers point, you can bring all the things that it points at along with you. So in some sense, that makes things easier. But distributed computing is a complex and different problem to solve. So can you bury that under the programming language, or is it inevitable that programmers have to worry about all of these issues? So in this panel, we'll try to address some of these issues. I'm going to sort of lead it off just because I wanted to, but I will also then hand it off to the other panelists to try to provide their insights and their views on these things. So I put up this particular slide very frequently because people don't realize that it was 15 years ago when we stopped getting faster processors, and you know, we said, okay, we'll just go multi-core. Well, unfortunately, multi-core has its own limits on scaling, that you get up to sort of 40, 50 processors on a single node, and a lot of things begin to get inefficient. And you know, there are ways to avoid those bottlenecks, but they do seem to occur, partly just physically. Memory is being shared across many different processors. That's a challenge, a lot of caching issues and so on. So fundamentally, our hardware has, you know, it was great for I had a long run with doubling every 2 years. I could sit around and my programs got twice as fast. Now it's a much harder problem. So we're trying to deal with that. This is an example of a programming language that has parallel computing built in. It happens to be a solution of the n queens problem. And so what are some examples of parallel computing? Well, some kind of parallel loop, parallel blocks, parallel evaluation of a recursive expression for things like Q-sort and so on, divide and conquer, and perhaps some notion of map reduce. And something I would claim, given that we're talking about safety and ease of use, is that to be a really true parallel programming language, you have to actually do compile time detection of data races. And unless they're totally impossible, and I would say one of the nice things about Rust and about the new Ada 22x features are that to some extent that is built in, that the compiler is checking that you're not passing data to two different tasks that could be running concurrently. And so the notion of ownership becomes very valuable here. The notion of global annotations about side effects and so on are very important to make it easy. I mean, it's certainly easy to just give programmers sharp knives and go at it, you know, create as many threads as you want and do whatever you want in any of them. But as far as reaching a wider audience, I don't think that's the right answer here. It's already hard enough to write correct programs in our sequential languages. So I believe the programming language has to help. And things like ownership and global annotations and that sort of thing is critical. Now, so we've begun to understand parallel programming, but as soon as you start writing parallel programs, you begin to realize, oh, well, I actually had a limit on the number of cores on my machine, and it would be wonderful if I had 100 or 1,000 or 1,000,000 cores. But at some point, you do hit some kind of a limit. And there are techniques for balancing all of your work, and so that instead of just having a very lopsided computation, you can balance it across the cores. But at some point, you do begin to run out of steam. And so that argues that we need to be thinking about distributed computing, and certainly with Amazon Web Services and similar resources available, and we've seen some of these very large supercomputers that are used for scientific computing, they're out there now, they're on the web. We should be using them. But if I have to spend my entire life rewriting my program and understanding all the ins and outs of doing cloud computing or doing scientific computing, that means I'm not really solving my problem anymore. So the question is, can we come up with languages or frameworks or technologies that will reduce the complexity of taking advantage of all of this cool new hardware? So just to kind of whet your appetite, you know, you get used to having maybe 20 cores or 10 cores on your machine, and that's really cool. But when the problem gets bigger, it would be nice if you know all these machines are out there on the network and they're probably pretty underutilized. And, you know, I've got something important to do. Why don't I just steal from all those other machines? And this is a little scenario where maybe you have 10 nodes with 10 cores each, 5 nodes with 20. There's one out there that's got 60 cores, but because of other reasons, it's sort of like it only has 50 because everything is a little bit slower on that machine. And you got a million things to do. Well, if you distribute it in a fairly balanced fashion, ultimately what was a single 10-core machine sitting on your desktop, you can now solve your problem 25 times faster if you can get a reasonable speed up. So that's a lot. I mean, something that took a day, you know, is going to take an hour, or something that took an hour is going to take a few minutes. And that's a significant. That's making when you get into 1 or 2 orders of magnitude, that changes what you actually think you can accomplish. So, and my last couple of slides here, I just wanted to introduce some of the challenges of distributed computing relative to parallel computing. With parallel computing, you start your program sequentially. This is where Amdahl warns you that all of your time will eventually be spent on the sequential part of your program, but we're going to ignore that for now. And then you fan out and you try to take advantage of all of your cores. You generate all kinds of work items. You share them evenly using work stealing and so on, and they all work away. And at some point they you know, sort of slow down. Okay, we've pretty well solved that part of the problem. And then you do a little sequential computing. Oh, okay, now we got a new parallel problem. And again, you may use up to 16 cores, let's say here, and then you're all done, which is great. But suppose in fact you only have 6 cores on your local machine, but you have neighbors who one has 4 and one has 10. You say, oh, cool. Well, I'm gonna farm out some of my work to them. And one way to do this is to start the same way, use sequential programming here, start fanning out and said, oh my gosh, I've used up all my 6 cores, they're all at full capacity. I've got plenty more work items. I'm gonna start sharing my work items with my neighbors. I'll send a bunch over to my 4-core friend, I'll send some to my 10 core friend, I'll send more to my 10 core friend, and then I'll wait for them to be done. I'll pull them all back together, and then I'll be back on my, I'll bring all this data back together and so on. And then we can do the same thing again. And that's, that seems like a sort of a natural extension to what we were doing with multi-core. But I would argue there's another way to do this. One of the challenges here is that we sort of find out, oh my gosh, I've run out of cores. Well, that's a little late to get things going on other cores, because you've got to start, establishing connections and waking people up and starting new processes and so on. And, by the time that happens, you've wasted a whole lot of time, and you could have just done it all. I'll do it myself or that, So there's another choice when you have distributed computing, is that if you know this is going to be a hard problem, you can start multiple nodes going simultaneously. And they can, in fact, all do the sequential part of your program. And they can, in fact, all do some of the fan out. But when they get to a certain level, they now do what I would call sharding the problem. Sharding is a term used. You break a database into shards and so on. Well, you can break a problem into shards in various ways. And now you're doing redundant computing up to about this point, and then you say, okay, well, I'm only going to focus on, this part of the problem. For the n queens, you can say, well, I'm going to only be interested in trying to place a queen on a board where I place the first queen on the first or the second row. So that might be this guy's job. This guy might work for the third and the fourth and the fifth row, and this one would take up the rest of the rows. And so they would be solving a part of the problem, and they would kind of agree in advance. Here in the early part, with a small amount of communication, they can agree, okay, I'm going to do this part of the problem, you'll do that part, and so on. And we'll do some redundant computing, but we won't have to communicate in the middle. We'll run fairly independently. And then at the end, we can pull it all back together. So these are two different ways of looking at the world from a distributed computing point of view. And that's my sort of current research activity, is to try to make that second view work in a seamless way from a programming language point of view. But I'm now going to invite our panelists, Kyle, James. Oh, James lost an S there. That's too bad. Sorry about that, James. And Richard to talk a little bit about their thoughts about both parallel and distributed computing and how the programming languages can help. Kyle, are you there?
I am, and I should be unmuted this time.
Okay. Feel free to share your screen if you had some slides.
Yeah. Oh, I clicked it too quickly. Okay. You can see my screen?
Yes.
Awesome. So I think Tak gave an awesome description there of the problems that are facing us on the distributed front. I think the big thing I wanted to say is that distributed computing is increasingly necessary for a lot of the people we're working with, but it's also increasingly inaccessible to users. And I think the end of Moore's law is one big reason why it's necessary. The other is that computational workloads, at least those that we're working with, are inherently changing. We're starting to see people deploying all sorts of crazy AI hardware. We're seeing TPUs, we're seeing people want to leverage FPGAs and things. So this world is getting more and more complicated, which is scary, because as I think Tak said in his description, we're already lagging behind from a language and interface perspective, being able to use the sort of commodity hardware now. I think GPUs, I think Xeon Phis, I think these large-scale distributed systems, without even thinking about the problems that are going to be facing us when your average scientist wants to tie FPGAs and TPUs into their workloads. So from my perspective, I'm very focused on the usability, the productivity perspective, because our users are scientists, researchers, postdocs, and students. They tend to value productivity, ease of learning, portability, safety, reliability, robustness. When I say robustness, I mean that something they write today is going to work a year or 2 years from now without them having to do anything. Some of them increasingly care about understandability, reproducibility, and a lot of these black boxy algorithms, a lot of these distributed workloads are becoming harder for people to reason about and reproduce and share with their colleagues. And that's sort of a cornerstone of research. Generally, I mean, I'm generalizing hugely here, but generally a lot of the people we work with don't care as much about performance. I mean, they care about performance to get their results within the allocation of supercomputing time they were given. They don't care so much about the elegance of their code. They really are just coding as a means to an end for them. And they really would just like to, as quickly as possible, code up their science app. So I think in general, we have fairly intuitive building blocks for expressing parallelism in code. I mean, we've just seen half a dozen different ways of doing it in the last couple of days. And the biggest challenge from my perspective is being able to enable these building blocks to be fairly seamlessly applied in distributed environments. So instead of focusing too much on the abstractions, I thought I would focus more on the lower level abstractions and some of the problems we see when we're we work with a lot of people that have something that works great on a few cores on their laptop, and they come to us and say, I want to now run this on 1,000 cores on a supercomputer. And so there's a bunch of things we tend to run into when we go through this exercise. The first is around location abstraction. So every node, every system you run on looks different. Getting that execution environment in any sort of homogeneous way is pretty difficult. Schedulers, there's different policies on systems. Parallel file systems cause us all sorts of problems. Heterogeneous infrastructure. The amount of times I work with someone that's confused as to why, when they move from a Haswell to a KNL, their performance has gone out the window. And KNLs tend to be, per core performance, tend to be, I don't know, maybe an order of magnitude slower. And of course, people view containers as the solution to all of life's problems, but you'll find the more you work with containers on these big machines, the less homogeneous they are. I mean, you can't even run the same container on two different systems, let alone thinking about how you wire in all the underlying libraries and things. The second is data abstraction. So of course, data needs to be available and accessible in different execution environments. Can we do this with shared memory? Should we be transferring data explicitly? If we're transferring data, can we work in a serialized object way, or are we actually having to materialize in files? Scheduling, which I think Tak described beautifully there, the when, where, what should be executed. Resource bottlenecks. Most people, or many people, struggle to diagnose the difference between running out of memory and running out of CPUs or cores. Obviously, competition, we start layering these different parallelism models. So I think this is maybe a little bit more unique to Parcel in that we layer sort of inter and intra-node parallelism together. And there, sometimes you end up with competition between these two approaches to parallelism. And of course, the more difficult ones that really, for us at least, are even further out there, thinking about robustness and resiliency, being able to, and I think that's a big topic that others will talk about here, being able to reason about these programs and make sure they're actually operating in a safe and robust way is incredibly difficult in a distributed environment. The last thing I wanted to say was Tak put this interesting question in his write-up about, would we ever want to specify placement in distributed systems? And so we're increasingly being asked by people to mix and match different types of parallelism in a single application, where they want to run multi-node MPI jobs for a simulation. They then want to do some multi-core, maybe use a whole node for training an ML algorithm. Then they want to tackle to add some high throughput inference, where they're taking that trained model, running inference on single cores, and feeding that all back again through some sort of reinforcement learning loop or some other machine learning loop. So these people are coming to us and saying, well, I've got this workload, I've got all these different building blocks, and I want to try and piece this together, where I want to co-locate bits and pieces depending on where data is, this whole vision of moving compute to data. So we have seen a few groups now, at least in our world, that are actually providing these ways of specifying node layout in their applications, where the two ways we've seen people at Brookhaven, they are basically describing an abstract resource requirement, where the language runtime determines how to put these things on core level placement. And then we've seen others, groups at Oak Ridge, that are actually doing a mapping. So for every program, they've got this map of all the nodes and all the cores and where they actually want to be piecing all the things that are running. I think our takeaway from these two approaches are that they're particularly complex and really accessible only to experts. I mean, from what we've seen, most people can't even accurately state the resource requirements of a job, let alone think about down to core level placement. And trying to describe a low level specification is fairly inflexible. I think that doesn't work for a fairly broad range of applications. So from my perspective, the answer to this question is no. Ideally, I would never want a user to be able to specify placement in a distributed system. And I would like to, as a discussion point here, is this something that we can actually automate or with sort of fairly simple heuristics put into the language or runtime level? That is all I have.
Okay, thank you. James, do you want to pull in something, or you could just react to what you've seen so far?
Sure, can do. Let me share my screen. Great. Yeah, so definitely I think there's the potential for languages to help us write more correct parallel or distributed computing problems. So I've mentioned, and it's been mentioned a couple things, that Rust has a couple language-based features which help address some of these lowest levels of concurrency and parallelism kind of approaches. Things like the send and sync trait, where the type system actually understands what types are correct to be sent from one thread to another, or sync types, which are allowed to be shared concurrently between different threads using things like mutexes or atomic variables and things like that, where you do kind of raise the bar of what your compiler is able to tell you about when you are doing things correctly or incorrectly, because it's very easy to accidentally introduce problems like this, particularly when a program hits a certain level of scale. It becomes hard for one person to keep in their mind, which means you're often looking at very many different parts of the language or parts of the application that you're writing, and it may not all click to you on the same day, or maybe you're just writing that code before you've had enough coffee for the day. So any way that we can have the compiler introduce these kinds of checks that can be done has tremendous value, because it doesn't rely on the user to just get it right or to remember to use certain review or static analysis techniques. There are also things in Rust like traits, which are similar to interfaces in other languages, that say this kind of data is capable of doing these actions. And this becomes really important when it comes down to abstracting certain capabilities, particularly serialization or communication, where you say, I want to be able to send this data over the wire. How can I not write a huge amount of boilerplate code for every single time that I pass data over the wire? And every time that I pass data over the wire, how can I make sure that it's done correctly and safely, rather than handwriting a bit or byte packing algorithm where you have the potential to overread a chunk of memory, or incorrectly serialize or deserialize, or write code that only works on a little endian machine and not a big endian machine. So these are the kind of things that help really deeply with abstracting over these functionalities, so that programmers can hold a consistent model of how these things work within their programs that allow them to better reason about the systems that they're building. Similar to send and sync, concepts like ownership and borrowing are another seemingly low-hanging fruit that can really help with the concept of, can I send this data from over here to over here, or can I have multiple threads working on the same piece of data at the same time? Things like work stealing queues are allowed to punch much deeper into these kinds of workloads, or even things like zero copy parsing or serialization have the ability to reduce or increase the granularity of concurrency that is possible within a program, that allow you to really more seamlessly leverage things like multi-core problems versus single core problems. And as a quick example, there's a work stealing queue library in Rust called Rayon, which I say is sort of a turbo button for parallelism, because you can take iterators over a single loop. So this is a sum of squares that's iterating over data, mapping it to a square, and then summing it. To make this a parallel work stealing algorithm rather than a single threaded sequential algorithm, it takes that much code change, because Rust can reason about what is sound to share between threads and not share between threads, which means you can turn that iterator into a parallel iterator with very little overhead and very little room for mistake from your developer. So there's definitely a lot of low-hanging fruit that allow your developers to build more complex abstractions that are specific to the kinds of needs that they have. Rust also has this ability to have AST-based macros, which allow you to extend the languages for specific use cases that are only relevant to you. So I mentioned the language ecosystem a little bit. So there's these languages that help you with parallelism or concurrency or serialization, depending on what you need. But specifically, I wanted to look at one use case. This is actually a framework called Arctic, which introduces a stack resource policy based approach to concurrency. So this isn't parallelism, but it is concurrency. And we can see these macro based approaches to extending the language, where we can write these sort of domain specific languages that only slightly tweak the language, similar to how tools like Parcel do this for Python. It's possible to extend the language itself so that people are still mostly thinking in the same idioms that they're used to, and they only have to, in one very small place, make these kind of conceptual changes that could possibly confuse them. And if they're just coming from a Rust background, this is still probably going to look fairly readable to them rather than a whole different language. So I really think it's important to balance this tendency of pushing these language supports further by looking at one of two different paradigms, where we're either extending existing languages and forcing people to understand sort of a superset of the existing languages they do understand, which is great for getting new developers in because they only have to learn these new superset of features, versus domain-specific languages which just say, we are different, but it helps people avoid that uncanny valley of, this looks like Python, but it doesn't really act like Python, or it looks like C++, but it doesn't really look like C++. So I have somewhat of a balanced approach here, that sometimes it's right to extend existing languages or build these into the language themselves. And sometimes it's good to just say, we're working with a different domain here, so it's important to break this into a different tool.
Thank you. Richard, do you want to give us a little of your insights?
You are muted, Richard.
You're still muted, Richard, so don't say too much more.
Yeah, I just saw they give me a notification about that. So yeah, this slide's going to give me PTSD. I was saying due to my earlier faceplant earlier today, but I kept this in here to make a point about this particular talk, and that is so I'm looking at this problem from a bit of a different perspective. We've had a lot of talk about kind of HPC applications where you've got this big workload and it's kind of like start and finish, and I'm looking at more of what I think is the future of sort of mainstream cloud-based applications, enterprise and consumer and these kind of things, where you have a much more static architecture for your application, and you're really worried more about scaling. How do you have this application that you can build and iterate on, but that you can also scale up and down dynamically with different loads? And I mean, so this is just talking about how you want to look at this problem architecturally. I think this is an architectural problem about where you're going to place certain components of this application you're building, what they're going to do, and so that you can replicate those individual pieces up and down as demand changes. And so that's kind of what that slide is just introducing. And sorry, my thing is lagging here, so that's no good. Hold on a minute. So the next slide I'm just going to jump to, and hopefully I can redeem myself a bit here. But so this is what we were trying to do with Zeros Apex. So now if you can imagine what we have here, so imagine that this white box is kind of like a fabric, or it could be fabric and it could also be TCP and UDP and whatever, but it's some kind of communication medium. And these boxes are your individual machines, or they're containers, or they could even be specialized inference devices or machine learning devices, these kind of sorts. And then within them, you've got these pieces of data which you're working on. You're doing something with it. And the point is that you want to be able to say, okay, this guy's got this job, but what if he gets too busy and we need to be able to respond to that. So you want to replicate that one. And this is usually done with containers, but as we know, containers, orchestrating containers is not as easy as it's painted to be from a theoretical point of view. And so, what we did here is that you want to have these they can all see the same queues on their own. So these yellow boxes, it's a global queue that everyone can see and everyone can access. And so these units can spin up and steal work from that queue. And when you're putting work onto that queue, everyone sees it and they can pull it on their own. And then when you notice that a queue is getting full or it's getting too empty, you could use that information to spin up instances to either produce or consume those things. So I think that the point being is that having a language or language features or language libraries that handle this sort of autonomous scaling in this autonomous sort of architecture in the background that allow you to build your solutions on top is really, I think, where we should head. And you really need a language that's orthogonal enough that you can build things on top of it logically and sort of go from these smaller scales up into the larger scales, break the problem down into the, you know, component parts so that whoever's working on that can understand that part. And then you can also look at it architecturally and understand the whole system. And so if you can provide support for both just that ability to really integrate design into the language, like you have with Ada, and that's kind of my plug on Ada, and then also be able to automate within the kind of language level that scaling in that work stealing model, and all of that mechanics that go behind it. That's my take on it. Thank you.
Thank you. So we're going to go back around, and each of the panelists is going to get a chance to react or to the earlier discussions. And I get to go first again. The moderator's right here. One of the things that I would notice is that I think in many application domains, there are sort of three levels of users. You've got the users who are sort of domain experts and really don't want to think very much about the programming problem. Then you've got the sort of middle ground who's building the tools and the abstractions and the so on. They know enough about the domain to know what some of the problems are. Or they talk to the domain experts and they say, oh boy, this really looks pretty tough for you. Maybe I can make your life easier. And then you've got the underlying infrastructure, the people who cannot think at all in terms of the domain. They think only in terms of the sockets and the messages and the, you know, blah, 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 blah. And I think all three of those people are important. And I think some of them are represented here more than others. And I think you need to accommodate all of them. They all need to be able to participate in solving a really big problem. I think today I'm personally focused more on the top level user, but also very much the middle level person. That is, if you want to be able to add to your language the notion of a distributed map, let's say it's sharded or partially replicated and so on, so that your top level users can very nicely just create a map and start putting stuff in it and having it automatically, you know, distributed and all that other good stuff. I think you want to have a programming language that can support both of those levels. And then at the bottom level, you've got to build all of the cool infrastructure to make that possible. So that's one of my comments. I think one of the challenges is the whole notion of not having the top level person have to write a whole lot of extra stuff. They want to just say, well, let's just solve this problem. But that implies that either there's a separate sub-language for tuning, and then they bring in the expert, the tuning expert. Okay, this algorithm is great, works perfectly, and it runs like a dog. We need some help, and you bring in your tuning expert who doesn't change the algorithm. In fact, you don't want them to touch your algorithm because you know it works and does the right thing, and I've certified it in various ways. But I want them to be able to twist some dials in a way that I would never figure out how to do. And I think it's very analogous to what goes on in tuning a car and so on. You know, I still want the steering wheel in the same place. I don't want to have to, you know, learn how to drive a new car, but I would love it to be a little more efficient. So I think the programming language can do both those things. The other thing, though, is the whole idea of automatic elasticity. And my daughter, who is online here, I'm happy to say, wrote her thesis about elastic databases. But the idea is that you automatically can scale up and scale down based on load. Another way of doing it is more sort of a batch mode where you run the program once and you monitor it and you find out, well, where is it spending all of its time and how things are actually working, and then you run it again. And of course, that doesn't really work in some environments, but I think in the scientific computing environment, they're often doing essentially the same calculation with new data. And if each time they do that, they can do better because they've gathered some information that allows some level in this layer cake to do a better job by automatically adapting its scheme or its location and so on. But I think I agree with what Kyle said and others that the top level person, the domain expert, really doesn't want to talk about, I need to put this data here, and then I want to have 4 cores on this node, doing this, And I think there was a question we'll come to, that what about these languages like Chapel and Fortran and X10 and so on, which were part of a DARPA supported language design process. Almost all of them do have the notion of, I want to run this at this location and I want to put data here. And, and certainly when you talk about OpenMP, I want to put data here on this GPU to try to, minimize overhead and so on. I just think we got to be able to support a level of user who never has to worry about that, or almost never. And so I think the language has to provide a algorithm, design and test level, and then some lower level things that let you tune it, build a better distributed map, and replace the old one with a new one. Anyway, so that's my take on this problem. Kyle, you want to weigh in?
Sure, yeah. Just always have to check all my mute buttons. Yeah, so I like your description there of the different roles that you see, the 3 different roles in the system, and I think I maybe am somewhere in the middle there. And I think probably many people here are, I guess. But I think you're right about the separation of concerns and this idea of the end user. Really, they have their algorithm. They've spent years or weeks or days working on their algorithm that they're very happy with. They know it does their science. They wouldn't want us poking around in that because we'll break it and we'll ruin their results. But what they do want is they want to come to, at the moment, they want to come to someone who happens to understand HPC resources and distributed computing, and they want us to magically tune that thing to make it all better, to make sure that the thing is running perfectly, it's scaling perfectly, that it's using all of the resources, it's not wasting too much compute time, et cetera, et cetera. And at the moment, for us at least, there is a lot of hand tuning there, that there's a team of people that know about specific machines and come in and tune the knobs exactly as you said. But we are very interested in trying to make that, and I think everyone here trying to make that a lot more automated. I think there's things we can do to, we do the same things over and over again, right? I think when we talk to people, it doesn't matter if it's a cosmologist or a biologist or whatever. Biology may be a little bit different because their apps tend to be pretty bad in terms of parallel file systems and things, but most of them are pretty similar in terms of what we're actually asked to do. And I think there are ways that we as a community can definitely automate some of that and improve that to a level where it would satisfy most of the needs. The extreme scale people, they're always going to want to do everything from the ground up, from the assembly code all the way through to their high level science code. But they're few and far between in terms of resources. I also like the way Richard described this underlying system level, and the thing that was sort of that was occurring to me there is it seems sort of crazy that we would all build similar implementations of that picture Richard has. That picture, if I squint and change some of the boxes to things that I know in Parcel, it looks pretty similar to the types of things we're trying to build there. And I'm sure it looks similar in Ada and other systems. So it feels to me like there's some building blocks that could potentially be shared, and then there's implementations on top of those building blocks that might be more vertical or siloed towards particular applications or communities, etc. I'll pass it on to whoever is after me. James, I think.
James.
Yeah, I definitely, when it comes to abstraction, I have a friend who has one of my favorite sayings, in that it's important to keep in mind the difference between simple and easy. And it's really common for a lot of people to build abstractions that are one or the other and not have a clear idea of what they're looking for. So his definition of easy means that it's very easy for someone to just push the button on the front of the machine and they get the result that they want. And this works really well until they want to change what that button does, or they want to tweak or tune what that button does. And when you've optimized for easy rather than simple, the chance of, like you're saying, if you've stratified your users into these 3 concrete blocks, then you're essentially saying there's a certain amount of wizardry that you need to understand before we're going to let you behind the curtain to change any of these parameters, which can be sometimes what you want if that's the aim of your project or things like that, but can also sometimes be very difficult because people will tend to use a non-optimal system because they go, well, I don't know how to change it, and we don't have anyone who works here who knows how to change it. I've worked at a lot of shops that had some magic C++ architect who used every language feature and managed to get everything working, and it worked excellently until someone wanted to change one thing and the whole glass palace shattered. And these are always really difficult things to clean up if you're not one of the wizards or the specific wizard that did that. One of the things that I think is really important is focusing on balancing when it comes to abstractions and what you're doing to make things easier for your users, is to think about the difference between, is this problem, or have I optimized this for simplicity or ease of use? Because simplicity can sometimes be more difficult, but it can make it much easier for people to graduate in terms of the ranks that you've outlined, or really just cross-learning knowledge, because many people are often experts in one field and totally new in another field. So it's not even necessarily that they are a different class of engineer, but rather that they've worked on algorithms, as you said, as scientists, but they've never worked on load balancing or databases or tuning and things like that. And as much as is reasonably possible, making sure that when we're providing these kind of systems, that we can, rather than just making them easy and say, it's dark wizardry, don't look behind the curtain, think about how we can simplify the system so they are more accessible for the data scientists to at least reason about what these systems are going to do, rather than necessarily always being able to tune every parameter of it. But that's one of those things where I see a lot of the time of this stratification of engineers, or putting engineers in a box of one or the other, or you are the architect, you are the senior, you are the junior. And it really pigeonholes a lot of engineers a lot of the time. And I feel like it tends to inhibit upward mobility and prevent people from introducing new good ideas about things that should be changed, or removing some paper cuts that have always been there. And you say, well, that's just how it is. But sometimes getting new perspectives on that can be really helpful in terms of going, why are we dealing with this paper cut at all? So that's the recurring thing that came up that kind of struck a chord with me of putting people in these different boxes and thinking about how we design abstractions to be more or less accessible rather than more or less performant, because sometimes it's easier to work with computers than it is to work with the people associated with them, in my opinion.
I'd like to just clarify my point here. I think one of my goals is that actually the same language can be used for defining new abstractions and using them. And that sometimes I'm in one mode or another, that is, I'm thinking about the domain, or I'm thinking about building a new abstraction. And I think I don't want to pigeonhole people. I really want to allow people to move from one level to the next. And maybe just today I'm worrying about the domain, and then tomorrow, that was a painful experience. If I had a better distributed map, I wouldn't have to write so much code. But I understand, on the other hand, if you have to use a whole different set of features to write the abstraction, then becomes the priesthood, and only the priesthood can write them. So I do think you want to make the job of writing those new abstractions something that is still also accessible to a wider audience. Maybe it's not as wide an audience as the people who can just, run at the top. I remember when I used to interview people and always ask them about a hash table. How would you, tell me about how you implement a hash table. And once the Java programming language came over, people said, well, I would pick the hash map, and I'd instantiate it or whatever. I said, you mean you've never written a hash table yourself? Why would I do that? I've got all these nice, and I think to some extent that will happen over time. You've never implemented a distributed map? Wow, it's such a fun experience. Why would I do that? It's, sitting on the shelf ready to go. And maybe that would be the future that we want. But anyway, I'll let Richard now chime in here.
Yeah, okay. I'm just trying to pick where we're gonna go with this. So I think for abstraction, I think this is a really near and dear to me. And I think when you're trying to reason with large systems, and again, I'm pulling away from HPC and like the scientific idea of having this big problem, and more towards your sort of practical application where you have a huge system that has a lot of people dealing with it and a lot of people with different responsibilities, and it's growing constantly. You're always adding new features and whatnot, and bug fixes. And so I think when you're going to have people working on the same project that are implementing something really kind of low level and specific and specific to their domain, but it's being used by people at a higher level. And I think it's kind of what we're really getting at with those layers of the users and the experts. And I think, to me, a lot of the existing languages that out there are really mute on this problem of properly abstracting things, not for the person who's writing it necessarily. That's done, but going a little further with it, running with that, and really trying to abstract things in the context of, like, I know someone else is going to use this thing I'm making. How am I going to make sure that they use it properly and in the way that I expect? how can I make the contracts that define sort of what's the okay way to use this and what isn't, without having to just like write comments and say, you know, this should be null if you don't want this, or this needs to be -1, you know, and actually have those contracts in some kind of a specification. And if you know Ada, that's kind of what I'm alluding to here, but having kind of a specification where you set out what you're offering and how you're going to do it, and then being able to start there and then dig down as far as you need to go and get, you know, split the problem up as much as you need to, and have that end user at the top not have to worry about any of that, I think is really key to sort of managing this growing complexity. And I think it's basically, to conclude, is I think it's super important that the language itself supports this ability.
Yeah, I definitely want to agree with you on that. I think that's one of the most powerful things that has been nice for me coming from a C background to a Rust background, is the ability to encode those invariants of your abstractions within the language itself, so that if your user tries to do something incorrect, then it just doesn't compile, because not everyone reads the comments every day. So having those preconditions, or something that can be checked by the type system, or something that can be checked by the borrow checker, or things like that, is certainly really powerful. And I think that's one of those really key things to consistency, is it's never a, oh, did you read this? Did you forget? It's just, did it compile or didn't it? And I think that's one of those really, really powerful, great equalizers. And I totally agree on that point.
If I may kind of just jump in a bit there, I think, and because I think there's a bit, like, while I agree with that, and I think Ada too is also well known for Ada users, is exactly the same thing. It's like the compiler is extremely strict, and if it actually compiles, it works. But there's a bit more. What I'm really getting at are things like, for example, in Ada we have something called a private package, for example. So you can have a component, a package that users can use, but part of the implementation of that package, you can make another package that's kind of underneath. But because it's a private package, the compiler will actually prohibit a user from even using that package ever. And so you have this extra safety where you can say, this part of it is for the implementation. I want to have a contract here that basically is that the user is not allowed to actually use this at all. And it's not, there's no way that they can put in like, no, I want to use this thing. They can't use it. And there's also ideas of like limited types we have in Ada too. So you can say, here's a type that I don't want the user to be able to copy ever. I don't want the user, you can go even further. You can make a type where it's limited, it's got unknown discriminants as a technical way of doing it, but you can say, I don't even want users to be able to define their own objects of this type without using my initializer or some other things like that, or maybe you don't even give them an initializer. For example. So I'm really talking about that kind of like really high level structural contract where you can define how your package or library really can be used. And by doing that, you can really give the user like, here's because it's language defined, they know these rules, and they know, okay, here's the package and here's what I can use and here's what I can't use. Without using comments, and then the compiler enforces it.
Yeah, I totally agree. Having a distinction between public and private modules in Rust, and public and private methods and public and private data structure members is huge in terms of enforcing invariants. And sort of like, unlike C, there's no way to just void star cast yourself into a private member. You know, you're going to end up not compiling and things like that. And this is something we leverage really heavily in the embedded ecosystem, where we have these abstractions where we have these zero size types that represent static items. So peripherals like your serial port or your SPI port and things like that, where we provide abstractions where you can only ever grab one singleton of this. And then we track ownership of those items so that you can only exchange those for more advanced abstractions or change it from a DMA mode to a non-DMA mode. And I totally agree. Things like that in Rust and Ada are definitely killer in terms of being able to encode those kind of invariants that a human doesn't have to check at manual code review time. It becomes a non-discussion because if you do it wrong, it won't compile. And Andrea Latituda has this term that he uses that says, building a hammer you can only hold by the handle. And I think that's one of those really powerful things in terms of enforcing safety, is make it impossible for users to misuse, because, and especially when you back that up with things like compiler errors that teach you what you have, something like an Elm language or a Rust language has, is that becomes an interactive code mentoring experience where you get it wrong, it doesn't compile, and it tells you exactly why it doesn't compile, or gives you the words that you can use as a new user to say, oh, okay, that's a private member, I can't get access to that. Oh, I need to use the public accessor function rather than the raw internal data, which may not enforce its invariant while the public method does. So I totally agree. And that's one of those things that's useful both for a safety and a teaching perspective in my experience.
Very, very interesting. I think that's the experience where the compiler becomes a tutor in some sense for the new programmer is very interesting. It can be, I mean, you had a nice picture of the guy reacting to the Rust compiler, hitting him over the head with, no, that's not allowed, that's not allowed, you know, sort of. I remember talking to a guy who was a C programmer who tried to use Ada, and he couldn't stand it because it just had so many, he was just always, you know, complaining. It just, all it does is complain, you know, and he said, well, if you actually get through all of that, then there's a good chance the program's going to do what you want it to do. You know, I mean, that's the observation. But I think maybe one of the points here is if you're building a really complex system, and most distributed computing systems are pretty complex, things that are not particularly related to distributed computing, but are just related to safety and doing things the right way and having good abstractions and so on, helps, because your life is simpler if all the clients are limited to doing things that make sense. And you know, Python is not a strongly typed language, but we do have MyPy now. I don't know if you guys are trying to use MyPy at all with Parcel, but we started using it in-house, and you know, I said, well, why don't we just add types to Python? But they did add the syntax. That's what I think is so interesting. They added the syntax for types, but type checking is all done by a third-party tool. So anyway, I think the general feeling is that the language can help in big ways and in little ways, and both are useful when your programs get really complicated. I did have a question here that I wanted to read. It says, from Rob Bacino, sometimes doesn't tuning require algorithm revision? For example, an algorithm that does lots of small reads and writes will never perform well in naive translation to a distributed context. It needs to be revised to send and receive large chunks of data. I'll say one thing here, and then I'll let others weigh in on this general issue of, you know, can you just magically take a program that is, you know, written randomly in some random language and, well, you push a button and, you know, it'll all be distributed? My experience is no, that, you know, the language probably has to raise the level of abstraction a little bit, get you away from saying the order in which things happen and where things happen and so on. I think it's in the programmer's interest to move up a level of abstraction, and we're not necessarily making it harder for them. We're maybe making it easier for them, but we should try to get away from making certain assumptions. One of the things that I did in the parallel language that I designed was, if you say for I in 1 to 10 loop, well, it actually doesn't do it in order unless you say forward loop or reverse loop. If you just say for I 1 to 10 loop, it generates numbers in random order. It hits 1 through 10, but it does it in a random order. And that forces the programmer to think about, well, did I actually care about the order? In some cases, a lot of times you don't. And so you sort of say that if you don't care about things, you want to be sure that you're not over specifying. And in a distributed computing environment, that's a real danger where you're over specifying. And so I think to some extent what Rob is pointing out is that there are a lot of languages where it's easy to over specify, not because you want to, but because you have to. You don't have any choice. But if the language can be moved up high enough level where you're not having to over specify, you're simply saying, this is the problem I want to solve, and these are some of the ways to solve it. And then the next level down and so on is where some of the details get filled in. So I think one of the keys to solving complex problems on, you know, really crazy hardware is to not try to over specify. Specify what you need to do to define what the algorithm is and that it's correct. And then, you know, sort of let the magic happens below. Of course, that's where the tuning comes in, is that magic may not always be doing the right thing. Anyway, other comments on this issue of, you know, having to rewrite or having to sort of push the programmer to not say things as far as tuning goes?
Yeah, I think this question from Rob speaks exactly to what I was complaining about with biotools. A lot of biotools do exactly what you say there, small reads and writes. They work great on someone's laptop, and then when you scale it, you get an email from an administrator of a supercomputer telling you you've killed their file system. So this is like, we run into this all the time. And I think there's different degrees of tuning. So I think some types of tuning are very automatable and can be, I mean, it's just basically a big parameter search type operation, which is great. Things like this, you're right. I mean, the way around that is, as Tuck says, that we shouldn't be specifying at that level if there are ways we abstract. I really like the analogy of the loop. I mean, if we can get people programming locally as if things were going to be sort of running remotely in a distributed concurrent environment, like your loop not being in order, people just assume it's going to be in order. But if we get these sort of constructs in local execution, then maybe it'll be easier for them to adapt to distributed execution. You could same analogies for reading and writing, etc.
Yeah, I sort of had fun when I actually made the compiler intentionally scramble the loop. And then I began to run into it down there. In IO, you generally care. Like I'm printing out some final list of the answers, and why are they all scrambled? I said, oh, because I didn't say I wanted forward. Anyway, I think the compiler could maybe help a little bit and say, well, you're doing IO, chances are you care about the order. But anyway, so we have 5 more minutes. This is a chance for people to weigh in with their summary statement of where they think languages should go to make our lives and make our customers, our clients' lives better. So Kyle, you want to give us your...
Oh, I haven't put much thought into this. I should have volunteered to go last. Although sometimes it's good to go first here because you can take other people's ideas. So where do I think? I mean, if I'm reading this correctly, I think the 4 of us are fairly well aligned here that a lot of this needs to be hidden from users. I mean, we've seen in Rust and Ada and others that there's a lot of great parallel constructs that already exist. I think I'm amazed to see the type of safety and stuff that you guys have embedded in your languages that really just make this so much easier. And I think for us in the Python world, to some extent, we're in the Wild West. We face problems as simple as type checking on a regular basis. And I mean, we're trying to MyPy all of our code base, but that's not a trivial endeavor. So I think the types of things you guys talk about, if we could bring more of that to our user community, I think it would be a real win. I mean, I think I said in my little write-up that, and I've said this probably 7 times today, that really for our community, it's about ease of use. It's about abstracting as much of this as possible, making it simple for people to express quite complicated things, and pushing all of the work to people like us that want to have fun on the language level, have fun on the systems level, to actually realize those opportunities and make sure things run sort of efficiently, quickly, safely, robustly, the rest of the words.
Okay, James?
Yeah, I just wanted to say that I totally agree with what you said, Kyle. I definitely think there's no replacement for systems engineering, if that makes sense. Systems engineering is totally orthogonal to programming language design, although they overlap a lot. But someone's always, at least when you're writing a systems programming language, someone's always going to want to do something really different and weird. And there's really no way to globally solve the problem for everyone. It's just a series of trade-offs and things like that. So I think it's always really important to remember that programming languages are just a tool and not the global solution for all problems. But that being said, programming languages can do a lot and can be a really good tool. But sometimes it makes sense to be proficient with a couple tools, because sometimes just the right tool for the job is different on each day, whether it's Rust one day or Python another day, things like that. I think there's a lot of room for understanding different tools in your toolbox and keeping that balance between improving the tool that you're working on and making the one tool that you know how to use the solution for all of your problems, because then you end up, putting screws in with a hammer, and that can be a challenging thing to do.
Yeah.
Richard?
Okay, so I'm in pretty much agreement with everyone. So instead of just agreeing with everyone, I'm gonna try to be a little bit more of take a I wouldn't want to say devil's advocate, but I think really, I mean, the idea that there's no magic bullet is kind of, I think, the agreement here. But I think I also see that this what's happening here, what we're seeing when you're dealing with the complexity of these large systems, of distributed systems, is that there's also a deeper issue that's sort of bubbling up, which I think is related to the history generally of software development, which is kind of came from a hacker culture. And there was this lot of interest constantly, like, I want to redo this thing. I got a new idea. I'm gonna, make this new thing. I want to do this fancy thing, and I'm just gonna, get it done as soon as I can. And there's this constant desire to try to like fix these problems by coming up with a new fancy thing. And I think that's actually a problem itself. And I think when you apply this to a distributed system sort of context, it can be it really rears its head in a way that's kind of hard to control. And I think it's important to have not just the language support for structure, because I do think distributed systems is really an architectural problem to solve. It's not something that the language is going to magically solve a lot of times. But I also think it's really important to have a language base that you can standardize, that you can really have a standard that is stable, a bedrock for people to work on. And not just having a standard, but when you go through that process of having that standard, it also adds in a little bit of requirement of the designers of the language to not go off on too many tangents and to keep things in line so that you can continue to sort of develop in a certain direction, which over time becomes this much more coherent framework at a large scale. If any of that made sense.
Okay. So on that note, I want to thank the audience for the attendees for coming. I want to thank all of the speakers and this panel in particular. I think we've created a lot of marching orders for ourselves as language designers and as language promoters, and as that there's much to be done, I would say. And I'm hoping a couple of years from now we'll all reconvene and have a couple of distributed computing languages we can talk about. I think it is possible to bring parallel and distributed computing to a wider audience, but I don't think we're there yet. I think there are a lot of challenges, and I do think programming languages and their sort of supporting infrastructure could be a big part of the solution. So I welcome, thank you all for coming, and I look forward to keeping in touch with everyone who has attended. So take care. Thanks a lot.
Thank you, Tuck, for putting such a wonderful workshop. Thank you
Thank you very much.
Thank you, everyone.
Thank you very much.
Bye-bye.
Bye-bye.
Yeah, bye-bye.
Thanks, Tuck. It was really good.
Yeah, awesome.
Thanks for coming.
For having me. I appreciate it.
Thanks a lot, James.
Thanks a lot.
Take care.